help us go through the questions in order. You can also use the chat feature, or there is a Slack channel, and you can use that for more detailed discussion after the talks. For the speakers, please do try to stick to your times. Total time is 40 minutes for each talk. And if you would leave at least 5 minutes at the end for questions, that would be really helpful. But in any case, the total time is 40 minutes, and I'm going to leave it to the discretion of the speakers, how you use up the time that you're allotted. So our first speaker is going to be Professor Philip Diamond. He's a professor in Manchester University, and he's a Director General of the Square Kilometre Array. And his talk will be on this topic. So the title of the talk is The Square Kilometre Array, a Physics Machine for the 21st Century. Professor Diamond, you have the floor.
Thank you, Professor Narayan. Can I confirm that you can hear me okay?
I can hear you. I don't yet see your slides.
No, so I'm about to share them.
Yes.
Okay, so you can see those.
Yes.
Good. It's the wonders of modern technology that I can talk to friends and colleagues in India from my home near Manchester in the UK. I'm honoured to be invited to give a talk about the Square Kilometre Array. I've entitled it, or the subtitle is, A Physics Machine for the 21st Century, because as well as undertaking major studies of astronomy, we will also, our user community will also be tackling fundamental physics topics, which I hope I will convince you of that fact as I go through these slides. So first of all, I'd just like to put the Square Kilometre Array in context. And I really do wish that I was 30 or so years younger, because 21st century astronomy will offer absolutely superb facilities for the young up-and-coming scientists. So the images on the screen that you see here are just a snapshot. It's not even the full set. So you see things like the Atacama Large Millimeter Array in the center of the screen, which is 64 millimeter sub-millimeter dishes operating in the high Chilean Andes. It's a joint project of Europe, North America, and East Asia. LIGO, I'm sure you're all familiar with, since in India will be building a LIGO station that's operational, producing superb results. The James Webb Space Telescope at the top of the screen is the replacement for Hubble, etc. You see it covers the full wavelength range. On the ground, we have the extremely large telescope. There are 3 of these, with India actually participating in one major project, the 30-meter telescope. And the radio cornerstone of all of this will be the Square Kilometre Array, which we hope to be entering full operation in 2028. So we're building these instruments to do science, and for the SKA, the key science drivers are, somewhat immodestly, the entire history of the universe. We will have the ability to do an enormous range of science. I think the broadest range of science of any observatory, even potentially any scientific facility. Looking all the way from the cosmic dawn, when the first stars and galaxies were formed, approximately 13 billion years ago, all the way up through the study of what we call the cradle of life, the birth of young planetary systems, biomolecules, the heavy biomolecules that form amino acids, which are a component of DNA, even the search for extraterrestrial intelligence. But you see it summarized on the screen here, and I'll pick out 2 of those topics to go into some a little bit of detail. I don't have time to cover it all. So we'll start with the dawn of the universe. Telescopes like Planck, which operated for 4 years, some years ago, observed radio waves from the cosmic microwave background. And this is one of the key results from Planck, which is an image of the entire universe, a snapshot of what it looked like 400,000 years after the Big Bang. Now, to put that in context, this diagram shows the evolution of the universe from the Big Bang on the left of the screen up to the present day, 13.8 billion years later on the right-hand side of the screen. And you can see some of the different phases, which I'll talk a little bit about now. But this Planck snapshot occurred about 400,000 years after the Big Bang occurred. And that's probably as far back as we can see with radio telescopes, because the universe is largely opaque in those early times. At these times, the Dark Ages, which you can see here, where there didn't seem to be that much happening in the universe. It's primarily neutral hydrogen, which traces the dark matter. So that's one aspect where we will be doing fundamental physics, is studying dark matter. But that will, the ability to probe that area will enable us to do precision cosmology. As we move into a potentially more interesting part of the universe, once reionization occurs, this is the time in the universe when the first objects will be forming and radiating. Stars, which of course form galaxies and black holes, etc. They will emit ultraviolet radiation, and feedback from these objects forming will heat and ionize the intergalactic and interstellar medium. Metals will form, shocks as stars explode, shocks will propagate through the universe. And the universe will reionize and become transparent. We'll see these first galaxies, and they'll all become visible. At the moment, we have some observations of this period of the universe, but they're extremely limited. The SKA will open this up, as will James Webb Space Telescope in a different wave band. So what we hope to do with the SKA is, rather than produce that static picture that the Planck telescope did, we hope, using the SKA and using its ability to study hydrogen, the most common element in the universe, of the first almost billion years of the universe, to make a movie of the birth, the dawn of the universe as we now see it. We'll also, of course, be able to carry on beyond that and study, the billions, trillions of individual objects that occupy the universe now. But this is one of the key scientific goals. And here's a little simulation of what we might look like. You can see a sort of Swiss cheese effect happening here. This is bubbles of ionized material growing as stars and other objects radiate in ultraviolet. They're all sitting in this sea of hydrogen. And this is a simulation by colleagues at the University of Toronto, showing how this might evolve over about 1 billion years. And you can see the universe becoming transparent in this process. Now, we, of course, won't be able to produce anything quite as photogenic as this, and it will undoubtedly be more complex than we imagine, but that's one of the goals of the SKA. Moving to another area, gravitational waves, which are, of course, a very hot topic in astronomy and physics now. Radio astronomers will use pulsars, the rotating remnants of supernovae, stars that exceed 8 solar masses, which have exploded. And you can see here the lighthouse effect simulated from the pulsar. And these are nature's clocks. nature has provided this network of clocks across the sky, incredibly precise clocks that we can measure to fantastic precision. I'm not a pulsar astronomer, but my pulsar colleagues are able to make use of these to study long wavelength gravitational waves. So this is a simulation provided by my colleague Michael Kramer from the Max Planck Institute for Radio Astronomy. And it shows our galaxy. At the moment, astronomers can detect about 2,000 pulsars, but it is expected that the SKA will be able to detect 30,000 pulsars across the galaxy. And in this simulation, you can see that they will map out the galactic arms. Within there will be of order 2,000 millisecond pulsars, and these are the incredibly accurate clocks that nature will provide. And so by looking at a selection of these millisecond pulsars across the sky with a telescope like the SKA, we'll be able to see the passage of gravitational waves. They will perturb the signals, the timing residuals that are observed by the telescopes from these pulsars. And therefore we'll be able to see the passage of the gravitational waves. We also hope, of course, to observe exotic objects, pulsar binaries. There is already a superbly studied pulsar binary. My colleagues hope to find pulsar black hole binaries in the galactic center, and extragalactic pulsars. But what will this tell us? Well, here, this is a very familiar diagram now of the first gravitational wave detection, and that, if you look at this spectrum of gravitational wave phenomena, LIGO operates at this particular regime, studying mergers of neutron star binaries, black hole binaries, etc. Space-based interferometers will look at low frequency, and then pulsar timing in a telescope like the SKA will study very low frequency objects. And you can see the sort of strain of the signal, the strength of the signal on the vertical axis. So SKA will be sensitive to the merger of supermassive black holes, those enormous black holes that lie at the center of galaxies, and also the primordial gravitational waves that come from the inflationary period of the very birth of the universe. So we will be very complementary with the SKA to other facilities to study the spectrum of gravitational wave astronomy. So how are we going to do all of this? We're going to build and operate the SKA Observatory. So we are a global collaboration which has now designed, and next year we hope to start building and ultimately then operating next generation radio astronomy observatory. A treaty has been signed, and yesterday it was ratified to establish the SKA Observatory. A little bit more on that in a moment. This is it's a new intergovernmental organization, very similar to CERN, and it's only the second such IGO for astronomy. But it's required for a project of this size, scope, and international partnership. We currently have 15 countries engaged, and we're hoping to bring more in with time. The observatory itself will have 2 telescopes, an array of almost 200 dishes in South Africa. I have photographs in a moment, and a low frequency array of 132,000 antennas in Australia, with a global headquarters in the United Kingdom, and a network of some of the world's fastest supercomputers. And governments are working to provide the almost 2 billion euros we need to for the first 10 years for construction and operations. So this shows our international partnership with our cute little mantra there. We are 1 observatory, 2 telescopes on 3 continents. That's where the 3 sites lie. You will see that India is a key player within the SKA. And in fact, the Department of Atomic Energy is the key agency with which we deal within India. So I'll come back to that in a moment. The sites. So here, this little globe is taking you to South Africa, which is showing where the SKA site for the dishes exists. We're not building on a virgin site. So our South African colleagues over the last few years have built Meerkat, and you see a photograph there. That's a real photograph, even though the dishes look far too clean. That's because they're new. We will fully integrate the 64 antenna Meerkat when it's complete into SKA. Critical issue here is that this is in the Karoo in the Northern Cape, and it's sparsely populated and therefore incredibly radio quiet. That's one of the key requirements for an SKA site. The other site for the low frequency antennas is in Western Australia, north of Perth. Now this is very sparsely populated. The area, the county, the shire in which we operate is the size of country, size of the Netherlands, but with a population of less than 100 people. So there's nobody out there, hardly anybody out there. And again, it's superbly radio quiet. Our colleagues in Australia have, stimulated by the SKA, put 2 telescopes out there and established the site. So the Australian SK Pathfinder, ASCAP, is operational, and the Murchison Wide Field Array, again, which India, the Raman Research Institute in Bangalore is a partner of, is a small telescope operating alongside ASCAP. So what are we going to build? As I said, 2 telescopes, single observatory. On the bottom left there, you see an artist in SK Low will look like. Actually, the station in the front, the 256 dipoles, is not an artist's impression. That's a real photograph. The ones behind are artist's impressions. So we will put 131,072 low frequency dipoles in the Murchison Desert, each dipole being about 2 meters tall and sensitive to low frequency information. This is a telescope that will do the cosmic dawn reionization studies. The stations will be spread across about 65 kilometers. In South Africa, we will build 133 dishes to add to the 64 Meerkat dishes, which already exist, spread across about 150 kilometers, sensitive to the range of about 350 megahertz to 15 gigahertz. This is the telescope that will have as one of its key science programs the study of gravitational waves. So this is what the observatory will look like. We have much more ambitious plans that I don't have time to go into. The total cost, I mentioned 1.99 billion euros. It's actually 1.986 billion euros that we're seeking over 10 years to construct and operate the observatory and the telescopes. Critical part of that is we require an observatory development program from the early days. We can't stand still. You can't build an observatory and never look to develop it further. The headquarters, it sits in this building in the foreground, in the shadow of the 76-meter diameter Lovell telescope south of Manchester. It's a beautiful location in the countryside, as you see. And this is the council chamber, which post-COVID, we hope to be back and occupying for governance and other scientific meetings. So the current status, well, we've had a very busy year. So we started, I take us back to August 2019 when the Netherlands ratified the SK Observatory Treaty. We've had a whole sequence of successful external design reviews, the critical design review of the telescopes themselves, operations review, an external cost audit, business enabling review, etc., with ratifications of the treaty occurring in between then. And then, as I said, just two days ago, we received the news that the Italy, Portugal, and the United Kingdom had finalized their ratification. So the observatory itself will be born as an intergovernmental organization on the 15th of January. We have a 30-day notification period that we are now engaged in. This is the signing ceremony, which was held at a lovely event in Rome on the 12th of March. India were not quite ready to sign the treaty, but they were. They attended this event and they signed what we call the final record of agreement. It's going through its processes within DAE and your government right now. So these are the 7 countries that signed, and these are the ones who have ratified. Our Chinese colleagues will be ratifying in early 2021. So this is it's fantastic to end the year in this way. As part of the current status, we're also preparing for our power procurement in both countries. We have grid power in South Africa, although it has to be supplemented by renewable power solutions. And in Australia, we have to, this is the power station, the renewable power station right now for the current telescopes there. We have to have something about 3 times as large. So we are proceeding down that power procurement line. We have SKA hardware prototypes on the ground. So this is the SKA dish prototype, which is funded by our German colleagues. It's different from the Meerkat antennas. It's slightly larger, significantly lighter, and from my perspective, great news. It's quite a bit cheaper as well. And as I said, we'll need 133 of these. And then this is, as you can see, a real photograph of the existing low station prototype in Australia. And we've been taking advantage of the lockdown period to do a lot of characterization and testing of this. We've been able to operate it remotely. So a lot of work been going on. Building the hardware is almost the easiest part of SKA. The data flow through the telescope is truly enormous. So summarized in this diagram, you can see the data rates internal to the telescope themselves. But coming out of the science data processor, and there'll be 2 of these, one in Cape Town and one in Perth, each 135 petaflop per second supercomputer, will be producing about 350 petabytes per year per telescope. A truly enormous volume of data, which will then be distributed around the globe, as you see here, to what we call SKA regional centers, which will be how the science users will interact with the SKA data. This gives you an idea, a comparison of the scale of the data. Now the Google and Facebook numbers are a little bit out of date, a couple of years out of date, but you still get a sense of the volume of data that will be produced and needs to be processed for the SKA. So we have a large, diverse software team that's looking at this. India's role in the project is extensive, been there right from the start. And in fact, this gentleman that you see here, Govind Swarup, who sadly died recently at the age of 91, was the initiator of the Indian participation within SKA. And you know, I was privileged to be able to know Govind over many years. And I worked very closely with his most recent successor, Professor Yashwant Gupta, who runs the NCRA in Pune. But you in India have a proud history of radio astronomy. This is the UTI radio telescope. I'm sure you're familiar. And of course, more recently, the giant meter wave radio telescope, which has been upgraded and producing superb science. And these are the various Indian institutes that have been participating in the SKA design areas. I think the key area is that India has responsibility for delivering what we call the telescope manager, the end-to-end observatory management system, which is going to have very sophisticated algorithms and software. It's the real-time control system of the enormous volumes of numbers of engineering components, but also the running the telescope operationally. So India has the responsibility to deliver that aspect. Very conscious that we take taxpayers' money to build these facilities. So just very briefly, as I come to an end, just wanted to talk a little bit about the societal benefits of the SKA. There are 17 Sustainable Development Goals that the United Nations has established. And within the SKA, we touch upon the ones that you see on the screen here. I recognize that we're not big enough to drive any of these, but we contribute, and we're very proud to be contributing to some of these Sustainable Development Goals. You may not be aware of the impact of radio astronomy. Within particle physics, you're very aware, I'm sure, of that there was a particle physicist that invented the World Wide Web. Well, accompanying that, radio astronomers actually invented Wi-Fi, which of course makes much of our access to the web possible. Early software developments for imaging translated across to medical imaging. We provide the reference systems for space navigation and GPS. The Earth doesn't rotate smoothly. It has little unpredictable wobbles, which radio astronomy using a celestial reference frame is able to measure and rapidly deliver that information to the appropriate bodies who make GPS work. And as a side benefit, we can also watch the tectonic plate movements of the planet, et cetera, et cetera. There's an enormous level of impact, and SKA is already adding to this and will continue to do so. There we go. So I just want to end. This is the overall timeline of the project. And I'm very pleased that we signed the treaty back in 2019. We've had our major reviews. We were interrupted by the pandemic, but our construction proposal and our observatory establishment and delivery plan was endorsed by our board in September. Major piece of work. The SKA Observatory now exists, and we are now just scheduling the first meeting of the council. And you can see this moves down to 2028 when we expect construction to be complete. So 2020 has been a year to remember for us for many reasons, or one that we will look back on in the future and think that was a difficult year. But I'm hoping 2021 will be a year to celebrate the birth of SKA Observatory. So thank you very much for your attention.
Thank you, Professor Diamond. So we are now open for questions. As I said earlier, please use the raise hand feature. That's the easiest way for us to know who is asking a question. So to start off the discussion, let me ask a question. So you mentioned that this facility will produce 700 petabytes of data per year. So is this data all going to be collected in central institutes? Is it going to be moved intercontinental? And if so, how exactly are you going to move the data?
So yes, it's an enormous volume of data, and it's a logistical challenge. But the data will be transmitted from the supercomputers. It's very expensive to store that amount of data. We will have one copy, but it won't necessarily be an easily accessible copy at the observatory. So we are working with our partners. We're setting up these what we call SK regional centers, And not all of the data will flow to each regional center, but regional centers will serve their regional community, and they will have access, they will have local copies of parts of the data, but access to the data around the world. And this relies heavily upon the modern undersea fiber optic cable network. So we're confident that we'll have access to 100 gigabit per second links from South Africa and from Australia to the various partner countries. And I was always concerned about the cost of this, but the cost is actually manageable. We estimate, and this is an informed estimate by talking to the providers of these infrastructures. We estimate it will cost us between $5 and $6 million a year to have access to the necessary infrastructure to deliver the data. So that's how we plan to do it.
Yeah, thank you. I think there's a question by Vivek Datar.
Yeah.
Please go ahead.
My question is probably, if I understood you right, you said that the SKA would be sensitive to gravitational wave radiation from very early times, from the Big Bang. Is that right, or did I get it wrong?
Well, potentially, it's as I mentioned, we'll be sensitive through for these very long wavelength gravitational waves that oscillate through the universe. Initially, until we build up our understanding of the systematics of the and understand the telescope in great detail, we'll be looking at statistical signals. But at some point, the aim with my pulsar colleagues, I'm just a stellar astronomer. I don't work within these very fascinating exotic areas of physics. Ultimately, they will be able, they believe, to detect many individual events with these long period waves. But I think that from the early days, they're looking more at the statistical signals from those very early days of the universe. That's my limited understanding, and I apologize. I don't know more about this subject.
Thank you.
So I had another question. You mentioned that one of the big goals is to make a movie of the early universe. I was wondering if you could say a few more words about exactly how that works. What is the signal, and how do you interpret and get a movie out of it?
So we will be looking at the emission and even the absorption against the background of the 21 centimeter line from neutral hydrogen, which of course is the most common element in the universe. Now, as one looks further out in the universe due to the expansion of the universe, that 21 centimeter line is stretched in wavelength. So the further back, the further away, and therefore the further back we look in the universe, the 21 centimeter line is stretched to meters, tens of meters, etc. And that's why it's the low frequency component of the SKA will be the tool that studies hydrogen in that early universe, the very red-shifted 21 centimeter emission line, which is red-shifted out to that period. Now, we will cover a frequency range of 50 to 350 megahertz, and therefore we'll cover a particular range of redshifts, and therefore about 1 billion years of the history of the universe. And we will be able to make maps maps of the large fractions of the sky. Ultimately, we want to cover the whole sky visible from the southern hemisphere. So we want to make images at specific frequency slices from 50 to 350 megahertz. It's a very complex process because we've got to remove all of the intervening contaminating sources. contaminating source to somebody interested in that H1 signal, to you and me, is stars and galaxies, which are very interesting in their own right. So it's a complex process to get there and to build up this. At one day we may have a true movie, but we will build up a view of the evolution of this this period, a fascinating period of the early universe. I hope that's a clear explanation.
No, that is fascinating and very clear indeed. And is this movie something that the instrument will get right away in the first year, or is it something that's going to require many years of observing?
It will require many years of observing, and it will also require a detailed technical understanding of the systematics of the instrument as well, so we can remove all the foreground sources accurately. But the simulations that have been done with smaller scale instruments now give us confidence that the techniques being developed now can be applied to the SKA with its enormous signal sensitivity, so that we'll be able to do it. But it's a multi-year program.
Wonderful. Thank you very much, Professor Diamond. I do not see any additional questions, and I'm not sure how we are supposed to applaud or clap, but please take our applause as given. Thank you very much.
Thank you.
So it's time to go to the next talk. This will be given by Professor Sheperd Doeleman, who is at Smithsonian Astrophysical Observatory and at Harvard University. He is the founding director of the Event Horizon Telescope and the director of the next generation Event Horizon Telescope. So his talk will be on the next generation Event Horizon Telescope, new approaches to black hole imaging. Professor Doeleman.
Ramesh, can you hear me?
Yes, indeed.
Oh, perfect. I'll share my screen. Oops, now I'm having a slight problem here. If I do this, are you seeing this presentation, Ramesh?
Yes, it's a little small, but no, it's probably okay. Yeah.
Oh, it is? I'm sharing the whole thing.
Okay.
Is it large enough? I can try to do something else if that's not.
No. I think I can see it. And yeah, please go ahead.
Okay. Well, so it's a pleasure to present to you today on the Event Horizon Telescope and the next generation Event Horizon Telescope. I really loved the presentation by Phil Diamond just now. And if Phil is showing you the after part of what a new telescope can be, about to break ground, this is at the very beginnings of a new telescope. And I remember participating in some of the early SKA sessions, and I'm really so glad to see that emerging as a global facility. So hats off to the SKA team. I'm going to talk to you about this idea that we have and had to image a black hole. And I think it's fair to say the Event Horizon Telescope started some time ago, asking ourselves, could we see what a black hole really looks like? Could we turn it into a laboratory for understanding general relativity? Could we turn it into a laboratory for understanding how black holes accrete matter and then drive cosmic outflows that can change the way the night sky looks? So really focusing on some of the fundamental physics, fundamental astronomical questions that we ask ourselves in modern times. So if you were to ask yourself what a black hole looks like, you'd be forgiven if you had been to the movies in the past decade and seen an image like this. This is from the Interstellar movie. And what this shows is the image of a flat, optically thick, cool disk that's orbiting a black hole. And there's many things that this movie got right, some things that, of course, it didn't get so right. But one of the things you'll notice about this disk is that you see the rear part of the disk being flipped up over. So you can't hide behind a black hole. the back part of the disk is being lensed above and below, so you get this characteristic circular feature. And then the thin ring you see is the actual photon orbit. That's the point at which light is constrained to move around the black hole in a circle. And when I say that this movie got things right, it really was grounded in gravity theory going back many decades. Jean-Pierre Luminet was one of the first people to visualize what this could look like. And you see here that if you had this cool disk orbiting a black hole, the rear part flips up and you get the image of the disk, but you also see this dark region in the center, and that's what we call the black hole shadow. And the size and shape of that shadow is directly encoded by Einstein's theory of gravity. If the black hole is not spinning, then the size of that shadow is the square root of 27 times the Schwarzschild radius. So just think of that for a moment. The square root of 27 times a handful of fundamental physics constants tells you what the size of the shadow should be at just around one of these supermassive black holes. And then if the black hole is spinning, you get a slight change in the size and a slight change in the dimensions of that shadow. So it's about 9/2 times the Schwarzschild radius. And a number of people listed here have done extraordinarily detailed work on what the size and shape of these shadows are. Now, it goes back almost 100 years. So I call the Event Horizon Telescope a 100-year handshake between what we are doing now and Einstein and Schwarzschild and the true pioneers. And back in 1921, Max von Laue drew this very prescient diagram. And you can see here that what we expect to see, while it is caused by the event horizon, shown here in black with its radius of 2gm over c squared, where g is Newton's gravitational constant and c is the speed of light, it is not defined by the event horizon. It's really defined by this radius, which is the photon orbit. And if you shoot rays back from Earth to a supermassive black hole, you'll find out that it is at this radius of the square root of 27 times the Schwarzschild radius at which light is confined to move around the black hole in an orbit. That's where it winds up being captured. So it's this size that determines the dim interior of this black hole shadow feature that we're after. And the modern thrust in computational astrophysics has been to simulate what this shadow would look like in many different circumstances. And one of the key differences between the interstellar image and what we are looking at with the Event Horizon Telescope is that the black hole is illuminated in fully 3 dimensions. There isn't a thin disk that's orbiting the black hole. There is an advection-dominated accretion flow, which was really, detailed by Ramesh himself, who's chairing this session. And it comes about because all of the gas is trying to get into the black hole. And for many of the supermassive black holes that we study, they are low luminosity. And what winds up happening is that the electrons and the ions differ in temperature. And much of the energy of the incoming flow is advected through the event horizon. We never see it because the hot ions carry it with them through the event horizon. And you wind up getting a very tenuous, but very bright in the radio emission plasma around the black hole. And no matter how you simulate it, whether on the left through a schematic mechanism, in the middle through spherical accretion, or on the right through very, very detailed magnetohydrodynamic simulations, you always wind up with this circular feature. And on one side is usually brighter than the other because of the near light speed orbital motions of the light around the black hole. And you wind up getting a Doppler boost on one side where it's coming towards you, and a Doppler deboost on the side where it's moving away from you. So you get an inherent asymmetry. So what we expect to see when we have near infinite resolution goggles and we look at the center of a galaxy and we see a supermassive black hole is a picture roughly like this. And our goal is to measure the size and shape of the shadow to test general relativity. So to motivate this somewhat, I want to take you on a tour of the galaxy Hercules A, and you can see it here in the optical, a smudge here in the center, and it's about 2 billion light years away and has a supermassive black hole in its center. And we know that because when we look in the radio, we see these incredible linear jets that themselves are about 1.5 million light years across. And they signify there is something that is incredibly powerful driving these linear outflows from the center of this galaxy. And of course, there's also a cooling flow which lights up this galaxy, and the X-rays shown here in purple. But the point is, how would we zoom in by more than a factor of 1 million to see what's driving these outflows? The only thing that one can think of that can drive these outflows is accretion onto a supermassive black hole. Simulations, this one done by Kaushik Chatterjee in the University of Amsterdam, show how this tenuous plasma that's orbiting the black hole feeds it, and then magnetic fields that are entrained by the black hole drive outflows from the north and south pole of the spinning axis of the black hole. So this shows what we can see with certain instruments like the SKA, and the Event Horizon Telescope is a specialized instrument to zoom in all the way to the center to understand how these flows are launched. So first I'll tell you about the results that we have so far from the Event Horizon Telescope. We targeted this object discovered about 100 years ago by Curtis, a linear feature coming from the center of the M87 galaxy, also known as Virgo A, 55 million light years away. And if you start to zoom in on this source, you see that this optical jet can be traced all the way to the center of the galaxy. So it's a miniature version of this much larger scale jet that I just showed you from Hercules A. And if you were to zoom in by a factor of 1 million from what the very large array can see here at 1.5 gigahertz all the way to the Event Horizon Telescope, you see that the jet is self-similar on many scales. So there's a two-sided jet, and you see one coming towards you because of the Doppler boosting. In fact, it's only offset from our line of sight by about 17 degrees. So the jet coming from this supermassive black hole is nearly right towards us. And you don't see the one going away, but you can see where it impacts the host galaxy on the left side here. And then as you go successively higher in angular resolution, now by a factor of 1,000, and then all the way up to a factor of 1 million, you see this jet goes all the way down to the center. And the goal of the Event Horizon Telescope was to resolve this central pixel here. And this is what we've done here. And to put this in perspective, to understand just in a visceral way how large this black hole is, this shows in a comic strip form where we fit. And it turns out that just the shadow of this black hole would encompass the entire solar system well beyond the heliopause. So we were truly looking at these monsters in the universe when we study them. Now, how do we get the high angular resolution that's required to do this? Well, no conventional telescope can make these kinds of observations. To put this in perspective, the largest black hole shadows that we can observe are about 50 or 40 micro arc seconds. So to put that in some other terms, it's as though you were able to see an atom held at arm's length. You'd be able to see an orange on the moon, or be able to read the date on a coin in New York if you were standing in Los Angeles. So these are extremely fine angular resolutions. And to do this, we disaggregate our telescope. We put radio telescopes at different parts of the Earth, and then they observe the black hole shown up here in the upper left. And the radio waves recorded at each telescope are time tagged with a hydrogen maser clock. These are atomic clocks that only lose 1 second every 10 million years. The waveforms are digitized and stored onto hard disk drives. And then they are taken back to a central correlation facility where they are compared. Now, this is exactly analogous to the perfect parabolic dish that in the optical, which receives a plane wave and then bounces all of those waves to a central focus where they arrive perfectly on time to be combined. And that's where you would put your camera. With the Event Horizon Telescope, we use this technique called very long baseline interferometry, where we freeze the light essentially on hard disk drives, bring them to a central facility where we recreate that nice parabolic dish, but in silicon, in a supercomputer. The signals that have been recorded are moved back and forth so we can find out exactly where they register with each other. And in so doing, we create a telescope as large as the distance between the radio telescopes on the Earth. So we're making a telescope that's virtual but as large as the Earth itself. And when we observe at a wavelength of 1 millimeter, which is relatively high radio frequency, in fact, the highest radio frequency that this technique has ever been employed for, then we get angular resolutions that are sufficient to image these shadow features. Now, the 1 millimeter wavelength is really important because before you get to 1 millimeter, if you are observing at wavelengths longer than 1 millimeter, the shadow is opaque. So this is a very nice simulation done by our colleagues at the University of Arizona that shows what the black hole shadow looks like when you start at longer wavelengths and move up to 1 millimeter. So at first the shadow is completely obscured, and you can see the jets coming from the north and south poles. When you get to 1 millimeter, this is the magic frequency where you can begin to see features on the scale of the event horizon. And you can see this is what we're after here, that circular feature in the center. Now, one last point about these data. To get the data back to the central correlation facility from this worldwide array that I'm showing you here, the only way really to do that is by sending hard disk drives in airplanes. One of my mentors, Alan Whitney at MIT, used to say that you can't beat the bandwidth of a 747 packed with disk drives. And it was true about 20 years ago, and it is still true today. We call it sneaker net, or we call it airplane net, but there's just no way really at the current time to get all the data volumes back that we record to the central correlation facilities unless we move them physically, although we are working to change that now with various satellite constellations. So getting back to the array, so in 2017, we were able to field finally enough telescopes around the globe to create not just an array that could image that could measure the size of a black hole, but one that could truly make an image. And we're fortunate that there were existing telescopes around the globe to do this. So we used the IRAM 30 meter here in Spain, 2 telescopes in Chile, ALMA and APEX, the LMT in Mexico, the submillimeter telescope in Arizona. We sent an intrepid group of astronomers down to the South Pole to install instrumentation there, and 2 telescopes in Hawaii. And together, this network truly does span the globe. Now, the other part of this that makes all of this possible is the fact that the Earth rotates. If we only had a few of these telescopes, we would only essentially get small silvered points on a virtual Earth-sized mirror. But it's really the connection between the telescopes that matters. Each connection between 2 telescopes, or a baseline pair, gives you one element of information for the image that we want to make. And on the right, you see the virtual aperture as it is filled in during a night of observing. So after about 12 hours, you have filled in enough of this virtual aperture so that you can start to make an image. And this is called Earth rotation aperture synthesis. Now, to make an image, we still have to understand that we have sparsely sampled this virtual lens. We can't have telescopes everywhere across the globe, so we wind up in a completely under-constrained problem. So when we minimize a term to find out how well we are imaging this black hole shadow, it consists of 2 parts. One with data, where we have the standard chi-squared minimization here, and another regularizer term where we enforce some constraints on what the image will look like. And typically these are soft constraints. They are mild constraints. They centralize some of the emission, but they don't dramatically tell us what we should be seeing. So we don't have ring priors, for example, that would force us to see a shadow. They're fairly gentle. And I want to show you roughly what this looks like. This is an animation of this process at work. So we start fitting the data, we use the regularizers, and then we anneal it there, and that's why you see that pushback, and then we come and zoom in again on the image as it forms. This shows you roughly how the process works. And it's a fairly robust process. To test this, we ran imaging challenges for a number of years within our group to find out how well these new algorithms that we were developing, these regularized maximum likelihood algorithms, could pull out these shadow features. So we created synthetic data with black hole images that we had corrupted with all the various error possibilities that we thought would apply to these data. And what you see here is 6 reconstructions from a mystery data set from 6 different teams, 6 different algorithms. And this was the input on the left. So you can see in this case, all of the teams were able to reconstruct with some robustness the input image. Now we have a case where not everyone agrees, and that's because, I have just hit the wrong button here, hold on. And that's because the input image was much more complex. It had much more wispy structure to it. So this allowed us to go back and refine these algorithms. And then every once in a while, we would throw into the mix something completely unexpected just to make sure that everyone was reporting faithfully what they were seeing. And this, of course, is what we know as Frosty the Snowman. Of course, we don't think that there's going to be a snowman in the center of the Milky Way galaxy or in the center of M87. But if there were, we're confident that our algorithms would be able to pull it out. Now, so that's the imaging side of things. And what really drove our ability to build this Event Horizon Telescope was a whole new generation of instrumentation. I think when I first started out in this field, we were recording on reel-to-reel tape recorders, and we had analog banks of filtering that allowed us to digitally record the data. And it simply wasn't enough, because when you go to high frequencies or the short wavelengths that the Event Horizon Telescope requires, your dishes necessarily get smaller because they have to be smoother. And it's very difficult to make large, smooth dishes. So most of the dishes that we use in the Event Horizon Telescope effort are of modest aperture. And we make up for that because the signal to noise ratio shown here at the top is dependent on bandwidth, the square root of the bandwidth, and not just the diameter of the 2 telescopes at either end of your baseline. And we were fortunate that there were enough 13-year-old gamers across the globe that drove things like graphical processing units and high-speed CPUs and large hard disks that we were able to follow Moore's law over time. So we made a decision early on in the Event Horizon Telescope to link our developments to commodity electronics, and that has paid dividends. So we started off here in the early 2000s recording on tape. We made the jump to digital. And then in the blue here, you see Moore's law increasing exponentially with the recording rate that would be possible at each site. And we've matched that. So we started off recording just a fraction of a gigabit per second. And now we're recording 64 gigabits per second, tracking Moore's law all the way. And that has allowed us to get the signal to noise ratio required to make these imaging algorithms converge. So in April of 2017, all of this came together. So our understanding of the theory, our development of the technology and its distribution to all of these sites, and we installed bespoke instrumentation at all the sites you see here, and levered these existing facilities to make this new instrument. And we also perfected these imaging techniques, which allowed us to have some confidence that no matter what we recorded, no matter what the data we recorded said, that we'd be able to image them. So we had an 8-station array with all the stations you see here. We had 5 days of exceptionally good weather triggered between April 5th and 14th. And we had detections to all 8 of our participating telescopes. So I'm not going to go into all the details of how we did this, but one of the key things is that we wanted to avoid groupthink. We had never imaged a black hole before. We had no ground truth. So we split the collaboration up into 4 separate teams, each of which used different algorithms, each of which had different ideas about how to approach the problem, but everyone was looking at the exact same data. And this is really a problem that one runs into in the sciences. How do you debias your investigators from the process? We didn't want to get into a situation where one team thought they saw a ring and that infected all the other teams. So there was complete independence. There was no communication between these teams. And we all came together at the Black Hole Initiative at Harvard University in the summer of 2018. And we were frankly astonished to see this. All 4 teams revealed the same general ring structure. And they had used different algorithms. Some used on the left the regularized maximum likelihood methods. Some used the clean methods, more historical radioastronomical technique on the right. But each saw this ring feature, and then we knew that we had something. And again, I want to stress that this has been a team effort all the way. This is just a small portion of the team celebrating after our second Event Horizon Telescope imaging workshop. And what's also important here is that there was an equal number of people on a speakerphone that were celebrating with us. But it wasn't over yet. We had to go through an image multiple days, and this was one of the elements of the project that showed us that these results were very robust. Not just that we saw the ring in one day, but that we saw the ring on 3 other completely independent days with different Fourier coverage, as you see here on the bottom in each of these. Now, in measuring the size and shape of the shadow and extracting physics from it, there are a number of ways we can do this. We can fit directly to simulation models. We can fit in the visibility regime, with fitting to the raw data themselves. What I'm going to show you here is how we do this with just the images. So when you take an image, it's easy to measure as a function of azimuth, the radius and the size of this ring. And you can see this happening here, and you develop a histogram, and you can measure what the size and the radius of this ring is. Now, for a Schwarzschild radius, for a Schwarzschild case where the black hole is not spinning, the angular shadow diameter, which is what we're measuring here, is equal again to a handful of constants. But the most important part of these constants are that we're measuring the mass over the distance to the black hole. We're measuring an angular size. And what's in parentheses here is what's commonly referred to as the gravitational radius, the angular gravitational radius. So we're essentially trying to measure this gravitational radius by knowing what the angular shadow diameter is and knowing what the constant of proportionality is out here in the front. But there's a complication, and I'm going to show you that with this animation here. Light takes different paths around the black hole. So some light paths are bent only slightly around the black hole, shown here in red. And we call this the n=0 path because it doesn't even make it one loop around the black hole. And you can see here a very tufty distributed emission that we would expect to see here on Earth. The n=1 emission comes from photons that go at least one U-turn around the black hole. Now these are lensed into a very tight ring that you see here that we call the n=1 ring. By the time you have photons looping around the black hole multiple times, then you get an extremely crisp ring that is reflective almost purely of the space-time around the black hole. It doesn't depend on the emission around the black hole at all. And when you mix them all together, this is when you get the true image that you should be seeing, which has the ring structure that you see there, but contaminated by all of this emission from astrophysics. So the question we had to face is, if we're measuring this entire region here, how do we elicit just this photon ring, which again is going to be related to the Schwarzschild radius. So to put this in another way, at the top we see a simulation, this one with a certain spin, with a certain ratio of electron to ion temperature, and we can look at what the true photon ring looks like, and that's shown here in white. But if we translate that to the image we actually measure, and then we take the ring that we extract from that image, we see that the extracted ring is larger than the true photon orbit. So there's some factor, there's some constant proportionality that we have to empirically determine. Now we did that by looking at 60,000 simulations, going through many simulations with different spins, with different electron temperatures and ion temperatures. And we looked for this constant of proportionality. We knew that the angular shadow diameter should be proportional to this, to the ring that we were measuring. And it turns out that after looking at 60,000 simulations, we were able to get this constant proportionality, and it was about 11.5. And note that if we were looking at the pure GR ring, that constant proportionality would be between 9.6 for a fully spinning black hole and 10.4 for a Schwarzschild black hole. So armed with this empirical scaling, and you see that here, we were able to determine what the angular gravitational radius was as a function of all the different days of the data we had, as well as different techniques. So in each of these days, we have a different technique here, and they all match to very high precision, about 3.8 micro arc seconds. So we wind up getting a mass because we know what the distance to M87 is. So remember, this was a mass over distant measurement. We know what the distance is, and we wind up getting the mass. And to within about 10 or 15%, we're measuring the mass of a black hole by laying a ruler across space-time. By measuring the size of this shadow, we measured the mass to be 6.5 billion solar masses. Now, what does this mean? Well, so far, I can summarize the results that we have. For M87, we have a ring diameter of about 42 micro arc seconds. We've derived a mass of 6.5 billion times the mass of our sun. It's circular to within 10%, which is what we expect because we're looking again nearly directly down the barrel of this jet that's coming from one of the poles of the black hole. So we expect from a general relativistic perspective for that to be very circular. And very importantly, there are other methods of measuring the mass of this M87 black hole using stellar dispersions, the motion of stars around the black hole. And the mass that we measure is very closely aligned with that. So there's a very nice correspondence with the mass we measure within just a few Schwarzschild radii of the black hole and the mass that people determine from stellar motions at much larger radii. It's not consistent with another estimate of the mass, which is the gas dynamics, which is very astrophysically interesting because now we understand that one of these models and one of these methods is not applicable to the core of M87. Now on the left side here, you can see that because of the asymmetry, because of the fact that the image is brighter on the bottom than it is on the top, that this is indicative of gas flowing around the black hole in such a way to come at us at the bottom and away from us at the top. And if you were to take your right hand and curl it so that your fingers are coming from the bottom of this image, your thumb would be pointing in the direction of the spin. And that's shown here. The spin is into the page slightly, and the forward jet, the one we see, is coming out of the page. So we've been able for the first time to measure the orientation of the spin of one of these supermassive black holes just by looking at the asymmetry of this image. Now for M87, our consistency with general relativity, the ability that we have to test GR, is limited by the uncertainties in the distance to M87, but also through this empirical calibration process that I talked to you about, in which we used 60,000 simulations to understand this constant proportionality. And that's one of the problems with this method, and we hope to refine that in the future by getting better and better simulations and understanding that empirical calibration. So for the remainder of the talk, I want to move on to what we're thinking of next. So again, we're at the early stage of understanding what the next generation instrument would look like, but it's really fundamentally based on this paradigm that now that we have very large dishes in the array, now that we have ALMA in the array in Chile, which is the equivalent of having about a 75-meter diameter dish, we can start to think about putting smaller dishes at many sites around the globe to fill out that Earth-sized virtual lens. And you can see here we're casting a very, very wide net. In fact, one of the sites we're looking at very closely is Hanle up here in northern India, which is very useful geographically to round out our array. And you can see here in blue all the sites that we're currently working with. And a number of members of our team have looked at the weather at all of these sites, trying to understand from a probabilistic point of view where we could put dishes that would be able to work together most of the time. Now, one of the reasons that we're able to do this is that we have these large anchor sites now. So ALMA, for example, in Chile, and the Large Millimeter Telescope are very, very large. And the name of the game in VLBI is to measure not just the amplitude, but the phase. And you can see here that I'm showing 3 baselines, ALMA to Chile to Mexico, Chile to Arizona, and Arizona to Mexico. And all you really need to understand about these images is that in blue you have the amplitude, and in the red you see the phase of the VLBI detection, which changes because of the atmosphere. The atmosphere delays the propagation of your radio waves, and you can change what the phase is as a function of time. But if we add all of these phases together in a round trip through all of these sites, then you wind up getting very, very good cancellation. This is called the closure phase. And you can just use effectively the strong site here, this one being ALMA, to phase stabilize the entire array. So now instead of being able just to integrate for a short amount of time over which the phase doesn't change, now you can integrate for long periods of time and increase your signal to noise ratio as the square root of time. So this technique can now be used with small telescopes, and that's really the key realization. So this graph here shows the kind of signal to noise ratios or the sensitivity we'll get not with a large dish of all of the variety that I showed you earlier, but with a 6-meter dish or maybe even a 4-meter dish. And it turns out by using these large anchor sites shown here in these curves in the bottom, we can achieve our target performance easily with modest aperture dishes placed ideally around the globe. So the reason that putting telescopes in the right place is absolutely critical is demonstrated here. What I'm going to show you is the best image we can make on the right using sites distributed on the globe on the left. And you can see when you have only one baseline, all you can really tell is how large the source is. If you add another baseline and start to fill out the virtual aperture shown here in the middle, now you can get a better idea of where the flux density is distributed, but you can't really see the shape. When you have an outrigger site, then you begin to see this ring feature for the M87 image. But it's only when you have the full array, incorporating the Spanish telescopes in Europe all the way to those in Hawaii, that you wind up getting the ring. So as with real estate, in VLBI, it's all about location, location, location. Now, when we double the number of dishes, if we were to take 10 or 12 6-meter or 8-meter dishes and put them optimally around the surface of the Earth, then you wind up getting this kind of array, and you get these kind of UV coverages for M87 and for Sag star here, and you can make snapshot images and movies. So this shows one possibility here. So we're seeing in red, in black on the left, all the coverage from just the EHT, and in blue, the NG-EHT. And we can now start to make wide field of view images of the black hole. And you can see here linking the black hole to the large scale jet. So we're aiming now at understanding how jets are launched. Now, we can do more than that. We can make movies. So on the left, you see a true relativistic movie of one of these black hole simulations. And on the right, this is what we can do now with synthetic data with the algorithms we currently can marshal. So we think it's extremely likely that we'll be able to make images of this quality for the first time linking the black hole directly to these outflows. Now for Sagittarius A star, which changes every half an hour, it's a black hole that's 1,000 times less massive, so it changes on minute time scales. The name of the game here is how much coverage do you have, as we show here, as a function of time. And if we merge two frequency bands at 230 gigahertz, where the EHT observes now, and 345, where it will observe with the next generation instrument, you can get very good snapshot coverage every 100 seconds. And here, we're not going to make a time-lapse movie, as we will with M87, but we can make a real-time movie. On the left, you see the simulation, which has been blurred to the resolution of the instrument. On the right is our time-resolved reconstruction. So with the next generation instrument, we'll be able to see not just the black hole shadow, but how it evolves in time. And that's important because the shadow itself tells you something about general relativity, but the motion of matter around the black hole gives you a much better handle on spin. And that's going to be very important as we think about extracting physical parameters from these black hole systems. And that's shown here. As I showed before, the black hole shadow is made up of different loops of photons around the black hole. And on the right, what you should really take from this is that the shape and the size of the shadow reflects spin and general relativity. So on the y-axis, you have the ring diameter, and then you have the ring asymmetry on the x-axis. And that also maps to black hole spin and the orientation of the disk that we're looking at. Right now, all we can really measure is this large ellipse. That's the precision of our measurements right now. But with the next generation EHT, we'll be able to be sensitive to much smaller regions in this parameter space. And we'll be able to tease out, we think, spin and inclination in the context of the Kerr metric that we think holds around one of these spinning black holes. And the last thing I'll point out on the science is that we think we can over-resolve. So we think we can extend to more and more sources. So this shows a technique that's been pioneered by Avery Broderick at the Perimeter Institute. And on the right here, you see the truth image. So in the lower right, you see M87, but now placed 3 times farther away. So we asked ourselves, what would M87 look like if we put it much farther away? And you wind up seeing the ring here with this jet moving off to the right. And with fitting techniques that can use high signal-to-noise ratio data to over-resolve by fitting a ring, we can get what's over here on the left. And in so doing, we can effectively increase the resolution by between 3 and 10, which increases the accessible volume around the Earth for our targets by between 30 and 1,000. And what that means is that if you look at the sources that are accessible to the next generation EHT, it won't just be Sagittarius star and M87, but we think there'll be a new population of sources for which we can measure the rings and test GR that will emerge and come into view. And so our basic timeline for this, again, we're starting off, is that we're in a design phase now, looking at receivers, backends, antennas, and subsystems. We hope to build out before the end of this decade and have first full observations by 2028. This is very much a team effort. I'm just thrilled and privileged to be able to work with such a marvelous team. We have over 200 members with 60 institutes across 20 countries and regions. And very importantly, there have been significant contributions by early career researchers. We simply couldn't have done this and even think about the next generation instrument without relying on the dynamism and the creativity of postdocs and early career scientists. And last, the human dimension. I think it's fair to say that there was an impact of this image. It was on the front page of most newspapers around the globe. So as we think about the next generation instrument, we are also thinking about science outreach. We're thinking about scientific literacy, and we're thinking about using the impact and of black holes and the interest of the larger community to tell a larger story about the importance of science. And hopefully that will translate into an increased awareness of issues like global warming and health across our globe. So this has been very inspiring to us, and I hope it's also inspiring to you. Thank you very much.
Thank you, Shep. That was fascinating. So we have time perhaps for one question. I think Amol has raised his hand. Please go ahead, Amol.
Hey, so you showed at this simulation showing that when you go down to a wavelength of 1 millimeter, the image becomes clearer. So what is the physics behind this? And does this 1 millimeter depend on the size of black hole, or does it's a universal scale?
Yeah, it's a great question. And Ramesh is really the expert here, but it turns out that in most of the accretion scenarios, the optical depth is a function of frequency. And that's just because of the emission mechanism, which is synchrotron. So as you look at longer wavelengths, you only see the surface of last scattering. And so you can only see the outside skin of this emission region. It's only when you get to 1 millimeter that the optical depth reduces to the point where you can see all the way to the event horizon. This has been seen before because when we look at these objects at longer wavelengths, we see much larger sizes. So that seems to fit very, very well. Also for Sagittarius star, of course, we're looking through our galaxy, and the interstellar medium itself blurs the image. So we have to look at 1 millimeter for that reason. Whether it's in a universal scaling, that it can depend on the mass accretion rate. It can depend on the mass of the black hole itself. If this is the base of a jet, there are scalings which alter with mass accretion rate and also with mass. So all of the sources may not have this exact sweet spot in observing frequency, but these two do.
Thank you.
I think I'll allow one more question. Vivek Datar.
Is Hanle really a viable possibility? Are there Indian collaborators who would be willing to push for that?
Yeah, it's a great question. So it turns out that Hanle is viable. We think there's already an optical telescope nearby. And people like Ramesh on the call here, and TK Sridharan, who's also an astronomer at SAO, where I work, have been pushing for this. So we are now in discussions with Indian collaborators on how to extend the next generation EHT to India. There's some wonderful, very good sites there.
Okay, thank you.
Okay, I think we need to move on. So thank you very much, Shep, for a very fascinating talk, and we hope it really will develop by 2028, as you have said, and I look forward to the movies. So it's time to move on to the next speaker. So this will be Professor Abhay Deshpande, who is professor at Stony Brook University, and he's director of Electron-Ion Collider Science at Brookhaven National Lab. So he's going to give a talk on Electron-Ion Collider, science, status, and invitation. Professor Deshpande. I'm not hearing you.
Can you hear me now? Can you hear me now?
Yes, now we can hear you. Yes.
And were you able to see my slides before?
Not yet.
Not yet.
We see your desktop.
Yeah, it's coming now.
Yes. So please go ahead.
Okay. Well, thank you very much, Professor Narayan. I want to thank the organizing group led by Vedanga for inviting me here for this talk. It's great to see some of the old friends on the video that I've met before in person. Rohini, Vivek Datar, Nilima Gupte. I wish I could be there in person. However, we have to live with technology because of COVID. Hopefully in the next future, we would be able to meet in person. It's always very difficult to follow up talks on astronomy and astrophysics because of the wonderful things that they produce in terms of visual imaging. The connection is now we are going from the mega to the micro scale. And as we go down in distances, Halina will also tell us even further down in distance scales at much higher energies. So I'm supposed to tell you something about the electron-ion collider, its science and prospects, and opportunities and invitation. So this project was approved in the context of the US planning process in 2015 by its National Nuclear Science Advisory Committee. The reports are shown here. This was the science that we produced in making the case for the science. And here was the report from the long-range planning that suggested that this project go forward from the scientific perspective. In the US, there is always an external evaluation of the project that is of this kind and this size that is done by the National Academy of Sciences and Engineering and Medicine. It's a very broad evaluation that not only looks at the science, but also looks at implications and uniqueness of that science and the project. So that result came out as a report, a consensus report from the National Academy that gave the project a final scientific go-ahead. And then two labs took over, Jefferson Lab in Newport News in Virginia, and Brookhaven National Lab in Long Island in New York. They produced two proposals And eventually, the DOE selected early this year, and I'll talk about that a little bit later, the proposal at Brookhaven National Lab to be realized with a combination of scientific ideas that came from the proposal at Jefferson Lab as well as what originated at Brookhaven. So the two labs are working together now to realize this project for the users, that potential users of the science. So today on my menu is that I'll give you some science highlights of the electron-ion collider. I will talk about the project and the status and plans, and I'll talk about the user group that has been formed to do the science eventually, who is now working to come up with the detector designs and forming and thinking about forming collaborations. I will end with the realization plans and timelines and opportunities and already involvement of the strong Indian groups that already has happened. So let me start with a very broad high-level background. QCD, quantum chromodynamics, is the holy grail of the quantum field theories. It's a nearly perfect theory, fundamental theory of quarks and gluons that embodies the nature's strongest force. It is rich with symmetries, and we all know these symmetries, and you probably have seen them in your graduate classes. What happens, however, is that the brokenness of some of these symmetries are the most important things. Most visible matter that you see in the universe emerges as a result of these broken quantum symmetries, and that is the aspect that we are going to explore experimentally. Inherent in QCD are some of the deepest aspects of relativistic quantum field theories, such as confinement, the asymptotic freedom, the various anomalies, and spontaneous breaking of chiral symmetries. They all depend on one unique feature of QCD, and that is the nonlinear dynamics. As we know, QCD distinguishes itself from QED by the presence of the gluon, the carrier of the strong force, which itself is colored, as against in QED, where photon doesn't carry any charge. So at the front of at the beginning, at the front, the distinction between the two being that the gluons can interact with themselves, whereas photons cannot directly at the leading order interact with themselves, and that's where the basic fundamental difference starts. And this nonlinearity, that multiple interactions with gluons interacting with each other, splitting into each other and for combining into each other, starts creating the difference that you see in the QED and QCD. This nonlinear interaction has very fundamental consequences. Emergence of spin and mass of the protons and the neutrons, the most stable fundamental particles that we have seen in the universe, the stable parts, the confinement, the gluon fields. These are all things that come because of these interactions that are nonlinear in dynamics, and I'll go through some of those things that will come through. The quark confinement, a unique property of strong interactions, is a consequence of nonlinear gluon self-interaction as well. The quark-gluon interaction is giving us some information, or we've seen this in confined motion of quarks and gluons, what we call transverse momentum distributions of partons inside the proton. We have clear evidence that these quarks and gluons are not stationary, of course, there is no reason for them. And we have evidence of that by seeing different left, right, up, down asymmetries with transversely polarized protons if we look at them. We also have evidence of the confined spatial correlations, which were embodied now in generalized parton distribution functions. They tell you the transverse position of quarks and gluons with respect to the assumed center of a proton or a neutron. All of these are deeply connected to the mass and spin of the observed of the building block of nature, which are these protons and neutrons. Basically form all the nuclei that we see in the universe, and everything that we saw in the previous two talks galaxies, and the entire visible universe comes out of those building blocks. And we are trying to understand the partonic origin of the properties that we see of the protons and neutrons of them. There is also a expectation in QCD, because of the self-interactions of the gluons, there is a prediction of creation of ultra-dense gluon fields. And the question is, do they really happen? Do they really exist? And if that does exist, then the theory says that it shouldn't be any different in nucleons and nuclei, which means that that thing that is created, which has QCD predicts has a very unique property, should be universal. Is it really universal? These are the kind of things that we are going to ask as we ask questions that are posed or unanswered questions in QCD. And to do that, however, it's not just the EP part that or EA part that I will be talking about, the collisions between electrons and protons and electrons and nuclei, but to make sense out of this, we also need to study nucleus-nucleus collisions, proton-proton collisions, and all of them should eventually, if we can answer those questions, should lead to the same answers. And this is really what I like, the universality of understanding of all these interactions. So these are complementary probes, what people are doing at LHC, what people are doing at RIC, and what people are doing with the electron scattering in the fixed target experiments which are currently going on, and what we would like to do in the future. So the emergent dynamics of QCD, I want to highlight that we are going to study this particle, the nonlinear particle, interaction particle called the gluons. Without gluons, there would be no nucleons, no nuclei, and no visible world. These massless gluons and almost massless quarks, through their interactions, generate most of the mass of the nucleons. And hence, if you look at this further, nucleons making all the atoms making all the observable universe. Basically, we are saying that the massless gluons and the almost massless quarks are giving rise to the mass of the universe and the properties that we see. We know that gluons carry about 50% of the proton spin. We know this very well from our experimental measurements in HERA, in DAISY. A significant fraction of nucleon spin, we now know, about 30%, comes from the gluon spin contribution. And about the same, 25% comes from the quark spin contribution. The rest of it is essentially something about the confined dynamics. It's all past aspect of the confined dynamics that we need to understand. The properties of the hadrons are emergent phenomena, resultant not only from the equation of motion, but also it is inextricably tied to the properties of QCD vacuum. And there are many examples that I mentioned to you before. Then there are questions about, if everything is confined in nucleons, then where are the nucleon-nucleon forces coming from? What is the partonic origin of that? There are various historical models for these, but can we understand these nucleon-nucleon forces inside a nucleus on a quark-gluon structure? That's currently not fully understood. These experimental insight and guidance is hence needed to complete our understanding of how hadrons and nuclei emerge from quarks and gluons. The method we are going to try to use this is a traditionally historic method that has given us a lot of information about particle physics in the past few decades. We're going to use deep inelastic scattering, where the electron scatters off of a nucleus with or a hadron, we're exchanging a virtual photon that is shown here with a star. And here, you don't have to go into details of this, but this Q squared is the momentum exchange in this collision, is a measure of the resolving power, how small a distance you will see. And that comes out to be only dependent on the initial energy of the electron and the final energy and the angle of the scattered electron. What happens in this whole thing can then be determined by further looking at some of the equations of motion, so not equations of motion, sorry, the variables y and x, which measure the elasticity or inelasticity and the momentum fraction carried by the struck quark. So by only looking at the final state of the electron, we are able to get a lot about what's happened inside this proton in that interaction. Of course, that's not the full story. In some other measurements, we also look at hadronic final state in certain phases, phase space of this xq squared planes to measure things better. But fundamentally, because we know the initial energy of the electron, we know a lot more precisely what is going inside the hadron in the electron-hadron or electron-quark or photon-quark interaction. There are various types of measurements we can do. First is called the inclusive event, where we have an EP or EA goes to E prime X. We only measure the scattered electron. That's called the inclusive deep inelastic scattering event. If we are more ambitious and start looking at also what happens on the hadronic side, if you look at the current jet that might be coming from here and what comes out as because the photon pushes some aspect out here, we see pions, kaons, and protons. That electron, scattered electron plus that part will mean that we are making semi-inclusive measurements. And if we are being much, much more ambitious, not only are we measuring the current and the jet, but also looking at what happens to the target remnant, then everything means that we are measuring exclusive measurements. And as you can imagine, to go from here to there, you need not only acceptance, but also luminosity. So this can be measured with low luminosity. As we go to that part, the exclusive part, we need a very, very high luminosity as well. The landscape of QCD now, with that precision of the electron scattering, we are going to measure is in this plot here. Here is the parton density increases in the right-hand direction here. That is the 1 over x or the x Bjorkane. And the resolution, the Q-squared resolution I mentioned to you before, increases here. Somewhere between this low and high Q-squared is a transition from the non-perturbative to the perturbative regime. And there's also transitions that might be happening which we have not explored or we have not seen from normal matter to these high-density partonic matters. And we have question marks on various things here. Also, remember that in the low Q-squared part, this is the strong coupling part, whereas if you go to the higher Q-squared, you get into the weak coupling part, where perturbative QCD techniques work. In this region here, it may not work. So in the extreme high Q-squared, all interactions are weakly correlated quarks and gluons, and that is well described by QCD theory in perturbative regime. In this part here is the interesting part that we don't understand quite as to because being non-perturbative, tools and techniques are not as sophisticated. Although ideas exist, we need to go and see them and emerge and go smoothly from regions of non-perturbative to perturbative in both directions, not only when the parton density is low, but also parton density is high. So this is the region where we want to do with precision and control. And as I mentioned to you before, at extremely high parton density, if we can reach a regime in which we are in weak coupling regime, then the perturbative methods that we know and we believe, we strongly understand, can be used. Then we can study this part of high gluon density or high parton density at extremely low X, predominantly gluon, and using the known and well understood techniques. So this is the reason why we want to do precision experiments in QCD using electron scattering with protons and nuclei. So these and such questions we categorized into 2 or 3 high-level pillars of science of the electron ion collider, which I show you in a glance here. We ask fun of questions. Let me just move this away. How do the C quarks and gluons and their spin distribute themselves in space and momentum inside the nucleon? How do the properties of the nucleon, such as mass and spin, emerge from the interactions of these quarks and gluons inside the proton and neutron? So here is the spin emergence from quarks to a complicated system of quarks and gluons. How does this spin emerge from these interactions? Similarly, if you take the 3 quark masses, it's only 1% of the total mass of the proton. Gluons are themselves massless. How exactly do their interactions make the proton mass about 1 GeV? Now in nuclei, how do color charged quarks and gluons and colorless jet interact with the nuclear medium? With the photon that I mentioned to you before, I can hit a quark inside a proton inside a nucleus and then see how the color interactions happen if this is an energetic quark now moving through the nuclear medium. Where does this transition happen? At the end of the nucleus, at some point, it has to pick up an antiquark and form a kaon or a pion, depending upon which quark was hit. How does that color confinement in the color happen in this interaction? It clearly holds the clues to the ultimate question in QCD of confinement, but we still don't have a measure to do that. If I change the size of the nucleus here, I can control how much nuclear interaction I allow or disallow in such interactions. And last but not the least, when I mentioned to you, when you take a proton and put it in the nucleus, the density of the nuclear environment influences parton densities inside the proton. How does that happen? How does that happen? And I mentioned to you again, at that extremely low, extremely high energies, we have seen that the gluon distribution from HERA that we have measured keeps on growing. And one of the reasons why we think it was growing is because the gluons being colored can split into 2 gluons, and these 2 can split into 4, and the 4 can go into 8, and this process can continue. And that process of continual growth because of the color charge has also to be looked at in the confined part of the proton itself, which means that at some point, a recombination process of gluons will start and to form 2 going to 1, 4 going to 2, 2 going to 1 again and again. So at some point, these 2 processes should be equal. At some point, that should happen. And that's the phase in which we think the gluon saturation will be reached. And the question is, can we see it? Can we actually see that happen in a future experimental observable? So let me give you a few examples of this. So we know that the nucleon spin can be measured very precisely by EIC, and I'm going to give you a demonstration of this a little bit with simulations here. We know that the proton spin is half, and it comes from the quark spin, the quark angular momentum potentially being there, the gluon spin, meaning gluon's alignment, and possibly whatever is the gluon's spin associated with it. And they are typically split into this for understanding. We know exactly how to measure the gluon spin and the quark spin and the gluon spin separately and together. I'm going to show you some pictures of that. We measure the G1 spin structure function. It's like the spin equivalent of the F2 structure function that more people are familiar with. And then through the evolution, so that G1 spin structure function tells us the quark's alignment and anti-alignment with the proton spin. And the evolution, the Altorelli-Parisi evolution of those gives you the gluon distribution from there. That's this part here. And here are some simulations as shown. This is the G1 spin structure function, and this is the variable x, the Bjorken x, the fraction of the momentum carried by the struck quarks. And in the high x region, the measurement and the data are very precisely known. We know this data very well, and all the theory, the curves are fit very, very closely packed. But as you go to lower and lower values of x, there is a large and large variation possible by the theory. And this is where in an electron-ion collider, we would like to go and measure very, very precisely these measurements here. And because of the evolution then controls the gluon distribution, the quark and the gluon contribution, the quark and the gluon contribution is shown here in the high X part, which is this part, versus the low X part, which is this part, which has we have no information yet. So as we go to higher and higher center of mass energy of a future collider, you would be able to go from the current uncertainties that exist like this to smaller and smaller uncertainties. Eventually, we would like to get to about a few percent uncertainty in all of these. I remember, but however, that we want to go in a future facility not only with the linear contributions, but the orbital contribution as well. We want to look at the proton as a whole in a 3-dimensional or 2+1 dimensional object. And fortunately, over the last 10 years or so, 15 years, these ideas, even how to make those measurements, have evolved, and the theory that embodies all those measures into a coherent picture has evolved. There's something called Wigner distribution that is that carries the momentum x, the transverse distance of the parton from the center in BT, and potentially transverse momentum distribution KT. And you can then connect them to transverse momentum distributions I mentioned to you before, the generalized parton distributions, which embody the spatial parameters, and then eventually what we are more familiar with is the parton distribution functions and the form factors. So you take this whole picture, and we think that we can measure in future experiments that all of these directly. And this is something that we would like to measure. Some of these things are not only important from the hadron structure point of view, but precision PDFs and the TMDs might also be very valuable for the future program at the LHC. So here is how we will measure the transverse momentum distribution of quarks. Here is the electron scattering off of a quark inside a proton, a cartoon, and with left-right asymmetries of pions or kaons being produced, we are able to now simulate the distributions of U quark with a transversely polarized proton and the distribution of D quark in a transversely polarized quark. This is the X momentum, and this is the Y momentum, and these are the kind of pictures that we will be able to measure. Similarly, for position distributions, we would have to measure through something called deeply virtual Compton scattering, a method of measuring a direct photon or interaction of a quark inside the proton that was discovered also at Hera in the Zeus and H1 experiments about 20 years ago. Now we can imagine that with transversely polarized protons or generally polarized protons, we'll be able to see the transverse spatial imaging of the C quarks and gluons inside there. I mentioned to you before that this is a plot that comes from Hera, where we saw a steep rise in gluon distribution that comes from these gluon interactions. And what we would like to see is this: is there some place in this future in the low X region where this saturates? Of course, if Hera didn't see it, we may not be able to see it with the program that we are planning to build, but we have something else in our plan. We want to measure it with the nuclei. And this is the nucleus, when boosted and explored coherently by the photon, gives an a to the power x 1/3 boost to the entire process. And we think that we can probably see this, the saturation region, which is critical in these future experiments that we are trying to build. And this is the part, the physics that I mentioned to you before, we are going to explore to see if there is really this transition from the steep rise to a saturation. All this science, now I want to put a perspective on the collider energies. I talked about nuclear structure and these partonic densities of extreme saturation of gluons just in the previous slide. We can do that science if we can start reaching energies of 50, 100 to 150 GeV in center of mass. The spin structure function that I mentioned to you before need to divide the data into multiple spin correlated data sets, and that's why we think about 10 times more luminosity is needed, and that's shown here, the luminosity of the machine and an integrated luminosity on the right-hand side, assuming about 1 year of operation of the machine. And the imaging physics that I talked to you about will require even further about 10 to the 34 in luminosity, integrating about 100 inverse femtobarn per year of operating. And if we do that, then we believe that we can do all these science components that I mentioned to you before, and they became the principal highlights of the science of the EIC. These were the scientific things that were evaluated by the National Academy, and they said the science was compelling, it was fundamental, and timely. Timely meaning that the technology, both on the detector side and so also the accelerator side, was getting there to be ready. And they recommended that the science, the machine parameters that we came up with and proposed in our what we call the scientific white paper of 10 to the 33, 34 luminosity is a good one to pursue, which is about 100 times or 1,000 times that of the Hera. The broad range in center of mass energy, somewhere between 20 and 100, upgradable to about 140 GeV. The polarized electron, protons, and light beams to study the spin structure very broadly. A broad range of nuclei, all the way from proton to uranium, if possible, so that we can study these gluonic, dense gluonic objects over a wide range in nuclei, and up to 2 detectors well integrated into the machine lattice. The X and Q squared range of the fixed target polarized experiments is shown here. This is the X and that's the Q squared. This is the region we would like to explore with this future collider. And that's what the range access that we will get to where the gluon goes. And here is a similar plot for electron nucleus scattering, which is shown here. And again, this is the region of gluon dominated region that we would like to go and see. Mind you, by doing that, we also increase our ability to study various physical phenomena, both in protons and neutrons and nuclei, in the Q squared direction. So evolution of parton distribution functions, spin as well as GPDs and TMDs can be studied very, very precisely over 2 or 3 orders of magnitude in Q squared evolution. Of course, if we are building such a thing, we are now exploring what else can be done. So there are new impact studies being done. What can we do with about 10 times more precise, limited only by the systematics of the detector, of PDFs? What can we help in the future endeavors at LHC? What can the TMDs play? What a role can that play in the W production studies at LHC? What can quark and quarkonia, even the heavy quarks, contribute to the QCD with about 100 to 1,000 times luminosity as that of Hera? And what can spin play? What kind of a role does polarization play in such physics? Now, interestingly, there are new things that have happened from LHC. We have discovered exotic quark systems. What can DIS add to that? We will be exploring that. And one of the important things is that the jets, which have become such a superb probe of high energy and nuclear physics at LHC and RIC, we want to study the structure of the jet itself rather than also only look at the jet studies with nuclear medium. So how do they evolve? How do jets evolve from very low energy all the way to 150 GeV in center of mass, which then can be continued into RIC at 200 GeV and the LHC regime at TeV. So we want to bring all of these together. And there are people who are now looking at pockets of regions where these high energy machines cannot look at, to look out for searches beyond the standard model. So such was the machine, such was the science goal. That was approved by the DOE. A CD0 was the scientific approval, came about a year ago today. The site was selected in January of 2020, and Brookhaven and JLab started working together as partners to realize this project. We are on a very fast path. We are expecting what is called CD1 to CD3 process, where CD1 starts with the technical design and CD3 starts with the construction in the next 3 years. It's a very ambitious timeline. And then we see that we can get the first collisions, just demonstrable, with the first detector ready somewhere in 2020, 29 or 30, with the operation of the machine starting fully for physics in 2032 or so. Here is what we are planning to do. The existing RIC rings are shown here, and to that we will add a possibility of injection of the electron beam. The red ring that you see here is the electron ring. It will collide with the hadron ring, the yellow ring, in two different places. The potential locations are the current location of the Phoenix detector in IP, what we call IP8, and the location of the star, which we call IP6. Currently, at least, the project thinks that this will be the first one to be built, and we'll see how that goes and how the second detector can be built. Of course, with the machine moving forward, we have formed a user group, the Electron Ion Collider user group. Currently, there are about 1,200 PhD members of it from 33 countries and 230 institutions. The world map of that distribution is shown here. And about 50% of them are from North America, 45% actually, about 30% from Europe, and about 20% come from Asia right now. Many of you are, I think I saw some of the familiar names to me, are part of this. We have the activities of the user group, the user group itself is very, very active. We have structures being formed. We have the steering committee, institutional board, speakers bureau, as well as election and nomination committee. We just finished a 1-year-long process, was something called the Yellow Report writing. Yellow Report, where the traditional name that is given for technical design studies that happen at CERN. So we picked up that name so it's transparent. Everyone in the world knows what a Yellow Report means for a design study. We just finished that activity, or just about to finish it. We have come up with some early designs of the machine. We have annual meetings. We started pre-formation at Stony Brook and then moved on to various places, and we hope to alternate between US, Asia, and Europe as we go forward. Here is a conceptual design of a collider detector that has come through based on this 1 year of activity, and I won't go into too many details, but a detailed rendering of that is shown in such a detector. You can see that it's an asymmetric detector, as you expect in an EP or EA scattering with hadronic side, much more carefully planned with particle identification, tracking on this direction, whereas the electron scattering, the hadronic part is there only for suppressing backgrounds, etc., etc. The detector extends much beyond the ±4 meters that are shown here. That's the fold detector I showed you before. We want to measure things that go very precisely in both directions, the small angle scattering of the electron, as well as all the hadronic and the nuclear debris that goes out here. And the close-ups of that make it a very, very complicated integrated detector into the machine lattice. We recently asked for international partners to express what they would be interested in. And I think we were very glad to see a huge 47 expressions of interest, each one of them with multiple institutions, sometimes followed by a full country. I point out for this audience, India was one of the most prominent ones among them on the map here, as well as in the contribution. I'll talk a little bit about that later. But here's an international contribution that came out. Of course, about 50%, 45% were from within the US, but we were very satisfied to see many, many other countries come through. And currently, at least, we think that non-DOE in-kind contributions of the order of $100 million are already expressed support by the various countries that are making these contributions. I want to highlight one aspect. This was a slide shown by our coordinator for software, Marcus Diefenthaler from Jefferson Lab. He highlighted the Indian involvement, which is probably currently the biggest involvement in the software consortium aspect of this. They're doing various important jobs that are necessary for designing and developing the detector and the interaction regime. And instead of giving names, because so many of them are involved, I just give the institutions. But this is something that we are very happy that is happening, and it's led by various people who are sitting in this audience today. So this was highlighted in one of the meetings today. I want to end with some pictures. Here is the, in September, We had the groundbreaking ceremony, as we call it, or launch of the project. Here is the EIC at Brookhaven, and here are the senators and the lab directors from both sides. President of the universities showed up to do that, and you can listen to that if you go to that web page that I showed you, you can see all the papers. I want to end with the summary and outlook. I think the electron-ion collider, a high luminosity polarized electron-proton and electron-nucleus collider, will be built in this decade and will operate in the next decade, in the 2030s. It will address some of the most profound questions yet unanswered in the standard model of strong interactions, what we call QCD. And if we are lucky, we'll go even beyond that with some unique aspects of even cracks in the standard model that might be observable with precisions that might come through. Up to 2 hermetic full acceptance detectors are under consideration, although currently the EIC project, as funded by DOE, only has 1 detector, 1 IR, and 1 machine. We are now looking for collaborations beyond that to see if we can build a second detector now, or we'll go do it a little later in time. The experimental collaborations to explore this will be found within the next year. The EIC project assumes a very aggressive timeline. It's supported by the 2 labs and DOE, the first collisions, as I mentioned to you, somewhere around 2030, and then full high luminosity polarization operation beyond 2032. There is already high interest in having international partners, both on detector and accelerator physics. I think the easiest way for people to get involved is to contact us through the user group, or contact me generally, or contact anyone from the project management who contributes to these the activities. I thank you, and I give you these 3 papers that were more recent ones that introduce the topic more broadly.
Thank you, Professor Deshpande. So we have time for just maybe 1 or 2 questions. I think Rohini, you have got your hand up. Go ahead, please.
Thank you. So congratulations, Abhay, for getting the project. I had one question about your use of TMDs in LHC physics. So these are because what I saw from this thing is that the polarized measurements will come much later, 2032.
Timelines are different. You're right. That's unfortunate.
LHC is not, going to be working till 2030.
I understand that. Yes.
This is a post facto effect, right?
That's correct. And probably one could argue, and maybe Halina will tell us more about this, is that I think the physics of that the TMDs and GPDs will really come in the 2035 timeline. So exactly. It's probably the LHC++ era that we will start becoming more collaborative. Currently, you're right, absolutely correct. But the same goes with the same goes with the precision linear PDFs as well.
Yeah.
Linear PDFs.
No, linear PDFs I understood.
Just so happens.
That I understood, but then I basically thought that
Yeah. No, I think you're right.
Can determine the PDFs quite well.
You're exactly right.
Okay, thanks, and thank you, Professor Narayan.
Okay. Yeah, I think we also have a question from Indumati.
Yeah, thanks. The question is about the polarization. I assume it's going to be longitudinal polarization. Do you have a number on the percentage of polarization that you will achieve in this?
Yes. So it's not just longitudinal. We have something called spin rotator magnets in both interaction regions just before and after. So we can do physics with transversely polarized, or single transverse, or this, or that, or that. So we can do the spin play is completely flexible. And the numbers the numbers are about 80% polarization in electron is used routinely at Jefferson Lab. We are careful about that because the ring is always going to accelerator is going to be difficult. We had reached about 60% polarization at Hera. So we think that we can get at least that, but there are things that we have learned from Hera quite a lot, and we can get off the order of about 70 to 80% in collisions very early on. So I think going beyond 80% is going to be difficult, even with most optimistic simulation studies, we think. But 80% is possible. On the hadron side, protons, we have at RIC we have reached about 60% polarization. We know where we lose the polarization, and I think the polarization is lost. The things that we are trying to fix are those things that we know how to fix. So my expectation is that not on the day one, but when the program gets going, we should be able to get about 70% or 75% polarization in protons. So 80% in electrons and 70% in protons is a good approximation to go for.
Very impressive. Thank you.
Thank you, Professor Deshpande.
Right.
Thank you. So I think we need to move on. Our last speaker of this session is Professor Halina Abramowicz. She's professor at Tel Aviv University, works at Atlas, and most importantly for this talk, she's head of the European Strategy for Particle Physics Update Committee. So Professor Abramowicz will tell us on future collider projects, the European perspective. Please go ahead.
Thank you very much for the invitation. I should say that, I am not anymore the chair of the European strategy because this one was successfully completed, and the CERN Council decided to update the strategy according to our recommendations. And I'm really sorry that, we have to use this technology for this talk rather than in person, which I would have appreciated very much. Anyway, so I'll start sharing now my screen. And then I will turn off the video because of I have an issue with the upload speed. So I'll come back during the questions. Okay. Just a second, because I'm really worried about the upload screen. I didn't turn off my video. Okay. All right. I hope this is okay now.
Yes. Yes, we can see the slide.
Okay, so I'll talk a little bit about the Future Collider project and the European perspective, which is basically, I'll lead you a little bit through the strategy process that led us to make some recommendations at the end, and hopefully they will be successful in the future. So I'll say a few words about the European ecosystem of research in particle physics. Then a little bit about the European strategy, and then basically most of my talk will be about trying to build the science case for the decisions and the recommendations that we made at the end. About the European ecosystem, so first of all, CERN is treated as being a national laboratory for all the member states, basically to all the countries, and this is most of the European countries right now. I presume that the similar situation is for the associate member states. The coordinating body for particle physics in Europe is the CERN Council, and this became sort of a natural body because most of the European countries are involved in it, and this is being treated as such by the European Commission. And this is one of the reasons why the particle physics community had to start building its own roadmap to be communicated to the European Commission. So the European strategy process recommends the roadmap for future research directions in particle physics, and it is supposed to take into account not only the European interest, but also the international aspirations, because we are becoming more and more of a global community. I was going to say, although, we are addressing only the remaining 5% of the mysteries that were discussed today. The challenge in developing this roadmap is to ensure the continuous success of this European research ecosystem, which is based on CERN as the main infrastructure for particle physics. which complements national laboratories, research institute, and university throughout Europe. This is another way to say that, you know, we always need to have a large infrastructure project to look forward to for CERN to survive. And for the 2020 strategy update, the main challenge was really to identify the optimal direction after the post-LHC era. And then taking into account basically the scientific priorities of the European community, but within the global context. And I would like to mention that I'm happy that Abhay had a talk before me, because the news about the EIC came pretty late within our strategy. So we managed to insert it in our discussion document, but we did not dwell too much about it. So let me just remind for those who know and present the concept of CERN. So basically, CERN has about 12,000 users coming from member states, associate member states, but also accepts observers and others. And basically, the money is paid mainly by the first column on the left, and all the rest is basically on basis of negotiations. But altogether, it's a very large community, out of which of the observer states are 20%, the others are 15%. And India constitutes, when I say 3% of the total, I mean the number of users coming from India which work on the scientific program of CERN. The budget of CERN is typically year after year about 1.3 billion Swiss francs, and India contributes about 1% now as an associate member state. Frozen. Okay. Now the CERN has an extremely rich infrastructure with lots of accelerator elements in it. And there is a whole area in which also nuclear physics is participating in. I mean, questions relevant to the nuclear physics are addressed, and then the particle physics sits here around the Large Hadron Collider and the SPS, where higher energies are achieved. And the structure, the governance of CERN is basically, as I mentioned, through the council, which has representatives from all the member states and associate main member states. It worries about the strategy, but also about the monitoring. The director general, which is elected by the council, basically has all the executive powers, and also has to manage CERN as a lab. And then there are various committees like the Scientific Policy Committee, Finance Committee. Then there are two others that you don't want to hear about because they're related to pension funds. It's a very difficult issue for CERN, but that's not the purpose of my talk. And then from time to time, the CERN Council may decide to call for a strategy update, and then a special body is being formed, like in the case of the strategy process in which I was involved. So typically, you know, this process of updating the strategy, or originally also the first time when it was decided, it takes about 2 years. So from the time when we convene as a group, we have to organize all the meetings, call for input, which is a very important thing. So the call for input to the future of I mean, the perception of science in the future is the basis on which we start debating the strategy. That whole discussion ends in the open symposium, which is dedicated to science. We try to keep the politics out of it as much as possible. Then this produces a briefing book where we summarize all the discussions. And then comes, we have the next stage, which is a little bit more political, where we have to draft the strategy update, make sure that all the member states are satisfied. And then there is a process of basically discussing in a closed circles within the council. And we were very successful that in June 2020, with some delay caused by the COVID crisis, the council decided to update the strategy. And there were two documents that were submitted to the council. One was basically all the statements that we made, and then the longer discussion, the deliberation document. And you have links here to the two brochures in case you're interested. So this was our final step. Basically, those were all the people who were involved in drafting the documents, and we spent 1 week in close quarters. So at the end, we ended up with 20 strategy statements, of which I will concentrate only on the third line, which is basically high priority future initiative. But just to give you a feeling, we also discuss all the activities which are also relevant to make the particle physics program a success, and it has also technical issues in it, social issues in it, educational, and so on and so forth. We have special working groups for that. I don't really have time to go into the details. Basically, the summary of all the statements is somewhere in my backup slides. So the way we started is basically something that was established at LHC, over almost 15 orders of magnitude, is that the standard model is doing amazingly well. So when we look at the proton-proton data, the Large Hadron Collider, I mean, all the cross sections are well within, the prediction of the standard model. And our only hope to maybe see some deviations is that, we still have relatively large uncertainties on the very small cross sections where we produce many, many particles and heavy particles, and which are supposedly most sensitive to the new physics that we are after. And also whatever we have learned about the Higgs till now seems to be very much like the expected in the standard model. So, but the Higgs sector is still the least known from all the sectors, together with the top. But I'll concentrate on the Higgs sector. And so there are basically two machines. I won't mention the EP here. The proton-proton machine and a possible electron-positron machine. And the difference is basically that the proton-proton machine usually has a very high statistics for extracting the Higgs, but it also sits on a very high, large background, while in an E+ E- machine, we have a much more direct access to the Higgs, also much less interpretations or assumptions about what we're seeing. On top of that, in a proton-proton machine, and this is related a little bit to what Abhay was talking about, not only do we need to know the structure of the proton, but we also have to have calculations to very high order in QCD to match the precision of the statistical precision of the measurements. In fact, it's a very frustrating stage because every time a new term is added, the cross sections move around. And so while we think we have a discovery, it turns out it's the theorists which have a discovery. I'm being a little bit mean, I'm sorry. And then, but in an E+ E- machine, on the other hand, because we understand so well the E+ E- interactions, we are much more sensitive to effects of new physics, but mostly in an indirect way. And for example, this is how we already knew about the top mass before it was discovered at the Tevatron, and we knew it was around 170 GeV. So this is but right now we have access to the proton-proton machine, and this is just as a reminder. Rohini mentioned it. In fact, the LHC program is going to be running up to about 2040, and the high luminosity LHC will start around 2027, around here. We are still preparing this phase, run 3, with this what is called the phase 1 upgrades of the detectors. There is still a lot of work to be done. And this is what we would expect concerning the Higgs properties by the end of the high luminosity LHC collection and data analysis. So so all these bars tell you basically what is the statistical uncertainty that we can reach. And in most cases, we basically manage to get below 1% of precision. The experimental ones are, as usual, very much correlated to the statistical ones, so they are of the same order. And right now the theory is leading, and as you see in some channels, really the theoretical uncertainty is the largest, with exception maybe in the coupling of Z gamma. So there is still more that we need, both on the theory side, but also on the experimental side. So this is just to flash the fact that, there is a lot of activity going around. The LHC right now also having in mind the fact that we would like to have an upgrade of the luminosity by about factor 10 within less than 10 years. And this, of course, we took into account in our prioritization. But so the standard model is doing perfectly well. However, not all is perfect. We know, for example, that neutrinos have masses because we observe oscillations. And there is still a very long way to understand all the properties, the mass hierarchy, the mixing, the CP, although there is a very rich program which is in line, and of course we support it very much. The other problem that we have is basically dark matter. We still don't have any candidate for the dark matter, but we know that it constitutes about 85% of the mass of the universe. So we definitely would like to be able to make statements about it. And there are more things which are not perfect. In particular, we also have the prevalence of matter over antimatter. The origin of it is not really understood. And then there is this famous hierarchy problem, which is basically a theoretical problem where the theorists are telling us that basically we are living in a very fine-tuned universe. This is a representation by Mr. Strassel, which I like very much, because what it says is that basically we seem to be living in a world like this, and if this vase is sort of hanging here, and to make it stable, we definitely need something to be handling. Otherwise, it should be either like this or crash. So but we have no indication of physics beyond the standard model up to the scales of the order of 1 of 3 TeV, the ones that we are able to reach at the Large Hadron Collider. And indeed, as I already mentioned, the top quark and the Higgs sector remain the least explored. So potential BSM effect. And then the question is how we should go about making progress. So this is basically our statement about, the road toward the new facility at the energy frontier. We basically established that, first of all, we need a new facility in Europe. This is more of a political than scientific statement. Of course, it has an influence of the science. And we think that the Higgs detailed studies of the Higgs properties is really the best way to go about, because the Higgs is a particle which is basically sensitive to all the content of the theory. We would recommend then to first start with an electron-positron collider as a Higgs factory, because we can also have there very strong constraints on the invisible decays of the Higgs. And then we should move to really large statistics experiments, also trying to reach the Higgs self-coupling measurements. And for that, we need energies which are significantly higher than that can be reached at the Higgs factory. And that, of course, will lead us to the future circular collider of around 100 GeV. But the physics conclusion is basically, let's start with the Higgs factory, but we will need more than the Higgs factory to get to the Higgs self-coupling, which has important implications on the development of the universe as well. And of course, whenever we go into new realm of energy, we always expect some mysteries to show up. So when the projects which were submitted to this strategy update process are shown schematically here. So I'm sure that everybody is aware of the International Linear Collider, which is an E+ E minor collider, which was, Japan offered a while ago to host it. This is more or less the plan. It's still not being approved, but there is a little bit of progress. We are in this pre-lab stage. I won't dwell too much about it. Then China has its own version of a circular collider, which is very similar to the one that CERN would be planning to do. This would be the first stage, an E+ E- collider, and then eventually followed maybe by a hadron-hadron stage. CERN is in a very privileged position because it has basically two options for an E+ E- collider, and then also a hadron-hadron collider. So one of the options that we were discussing is the CLIC, which is a compact linear collider, which with time could reach basically 3 TeV center of mass energies. And then there is the future circular collider. This is basically a 100-kilometer tunnel which would be somewhere under the Jura, under the Lake of Geneva, around CERN. And it may have a very rich program, which starts, for example, with the E+ E- collider, which can have very high luminosities at low energies, and then can move then towards first 100 GeV hadron-hadron collider, and for that we need the development of 16 Tesla magnets. That's why it's favorable to push it a little bit further in time. But if we were to get to 20 Tesla, then we could even dream about 150 TeV hadron-hadron collider. Now, the point that I wanted to make is that when people talk about the future circular collider, and this will show up in some of the comparisons that I'm going to show, in fact, the program includes not only an E+ E- machine in the first stage and the hadron-hadron in the last stage, but also an intermediate electron-hadron machine. There is not much talk about it, but basically what Abhay was talking about is very important, that we cannot use a hadron-hadron machine without having precision knowledge for precision measurements if we don't have precision knowledge of the proton structure. So there are also optional here. You can see. I won't discuss the high energy LHC. It was not very attractive. And then there are also in the background options where we could, for example, shoot an electron beam into the LHC, having a high energy electron proton machine. And this is the stage of the FCC that I mentioned, where also we would collide electrons and hadrons. So this is what we had to discuss. So those are the various configurations. Maybe I won't be spending much time on that because the time is limited. So let me just repeat that then we had to make a decision, which way do we go? Do we go through electron-positron on proton-proton? And then, of course, the technical aspects of this proposed facilities was reviewed in detail by experts. You have all kinds of numbers here about luminosities. All in all, they all resemble themselves in the electron-positron range. Of course, the hadron-hadron offers much more center of mass energy. And there are still, issues that are important to solve, like, for example, the high field, the superconducting magnets. But as we were told, this is on a scale of 10, 15, 20 years. There is nobody sees showstoppers for the time being. So the next step was, since the technology was not, a good option to start differentiating. So we had a whole working group analyzing the reach of the various machines for precision Higgs measurements. And if you look into detail, wherever you look, you always see that at the end there is this little bar in black, and this little bar in black is basically the whole FCC program, which includes the E+ E- stage, the electron-proton stage, and also the hadron-hadron stage. It doesn't mean that there are not other machines which compete in some ways, but by far, because of the high statistics that can be collected at the proton-proton machine, and the constraints coming from an E+ E- machine earlier and from the electron-proton, then this combined program wins it all. As far as the Higgs self-coupling is concerned, then by far this combined program in FCC is the best, and can not really, the other machines cannot really compete very much. Maybe further stages of ILC and CLIC would be competitive. So then, for example, if you look at the search for dark matter, so now we are looking at, for physics beyond the standard model. Again, here are, for example, the reaches for the dark matter candidate. And again, you can see that basically when you combine all the FCC, so the highest reach is basically achieved with the FCC, although in some aspects also an electron positron machine would do. This is another way of representing it, where this is compared now to all the experiments which have for the direct manifestation of the of dark matter, and you see that we are the hadron colliders are very complementary for low mass and low values of the coupling constant. So this is good. In general, you know, there are so many options in the beyond the standard model physics that it's very difficult to present it all. But again, the hadron collider fares quite well in terms of the reach in scale that you know, of the new physics. There are some areas in which, of course, like in the contact interactions, that the precision measurements at the plus and minus collider are sensitive to some of the couplings. And here on the right side, you see this is again another representation of basically the exclusion area. And you should see also this orange curve, which would be the best, of course. This is a muon-muon collider at 14 TeV. This assumes that, of course, it will fit into the LHC tunnel. So unfortunately, the discussions about the muon-muon collider we didn't have enough details yet to be able to treat it as a machine of the future, although, of course, people are dreaming about it. Okay, now I'm stuck again. Okay, so the conclusions for the high priority future initiatives were that basically we have two ways to address the remaining mystery, the Higgs factory and an exploration of the energy frontier. So as I mentioned, you know, Europe is in the privileged position to have basically the two options can be realized at CERN. But eventually, because of the increase in energy which comes with the future circular collider, this was deemed to be the most promising facility for the future at the energy frontier. But of course, we are realistic, and it's a project which has many technical and financial difficulties. And so our recommendation was to basically conduct a feasibility study to make sure that if we embark on the project, we can complete it. Okay. Now, one thing that I would like to mention, because this goes beyond, you know, the near future, this is the fact that we need to invest into development of new accelerator technologies, because we are getting to the limit of what really makes sense, or where we can argue that we can achieve it. And also, you know, by developing technologies, we are very likely also to help the society in many aspects. So we also put a lot of stress on that. And, you know, there are two examples. So one was, for example, the muon collider that I already mentioned, which is a much smaller infrastructure, maybe not financially as it turns out, but at least, you know, topologically. And of course, there is a lot of efforts going now into Wakefield plasma acceleration. And, you know, there is a lot of challenges, of course, but if we don't invest in it, these challenges, like, for example, forming the beams, will never be met. So this was also our very strong recommendation together with the feasibility study. So I wanted to mention the fact that, you know, our accelerator R&D remains crucial for the preparation for future collider programs, and this has to do both with superconducting magnet, high temperature superconductors, for example, for the magnets, but also new technologies. And so we want to make sure that nothing is left behind while everybody concentrates on the future circular collider. So my concluding remarks are then that we are looking forward to a positive conclusion for the future circular collider feasibility study, because then we know for sure that we have something to look forward to. Europe will participate in any future electron-positron collider anywhere in the world. An important thing is that given the scale and the long-term ambition, the European plan needs to be coordinated with other regions of the world. It remains important to explore novel accelerator technology, I will repeat there, and a further update of the strategy and maybe redirection or maybe not is to be expected around 2027. We do it every 7 years. Thank you very much. This is the end of my talk.
Thank you, Professor Abramowicz. So we have time for a few questions. So please just raise your hands if you have any questions. So I guess I had a question. This 2027 next update, when will that start? Will it be kind of 2 years earlier?
Typically, yes, that's what happens.
And so what, yeah, I was just wondering, what developments do you expect to happen between now and say 2025, which would have an influence on what the next update says?
So I think the most important one is to make sure that the magnets, the high field magnets, can be produced for a reasonable price on a reasonable time scale and can be industrialized. I think this is a very important issue. And this is where, basically when you talk to experts, that's why we recommend, in fact, a roadmap so that we have a statement on which the experts agree. The time ranges can be differ by tens of years. So this is, I think it's very important too. And the other thing is, this is basically what the Director General Fabiola was asking for, is that, we still don't know whether the community around CERN would like to have infrastructure of this size, because now we are basically going far beyond just the CERN area. So there are things like this. This is what I call the societal issues, and if we start, those are long processes, convincing the community, finding out whether this is physics, the geological studies, all these aspects as well. So those are basically, they need time. They are not very costly, but it's better if they are explored before we make a decision made based on, let's say, the scientific part on which we have more influence.
Yes, thank you very much. There is a question. I think Rohini has a question. Please go ahead.
Thanks. Not really a question, but I just wanted to ask Halina that the US, for example, and as you know, it's now embarking on its NOMAS exercise, and also we should know presumably about CEPC status. That's also evolving somewhat fast. And what do you imagine would be the impact of these two processes? I mean, that would be really one more very important input that would go into the discussions in 27. Would you agree?
I'm sure. But we had a very strong encouragement from our sort of collaborators from the United States, and this went beyond sort of just the physicists, that they would be interested in contributing to this energy frontier machine. I think that also our Japanese colleagues get a very strong support for the linear collider. I think it's also important that we demonstrate new technologies. It's there is this fight. I mean, circular means more experiments. Do we need more experiments? Maybe one experiment is enough, for an accelerator. There are all these discussions going on. But at the end, I think that we are so hungry for a new facility that whoever comes with the first facility. And so of course the United States is going to be a very important partner in this.
The reason I sort of made that statement was to some extent answer Professor Ramesh Narayan's question, that there are these very important inputs that are going to come from the global community, which would also go and affect the decisions that would be happening. But I was also very nice to hear from you. I had sort of heard this, that the American community is quite strong on supporting the energy frontier. So that's a very good piece of information to have. Thank you.
On the other hand, we hear that maybe the muon collider is taking traction now in the United States. It would be great if, for example, there is also support for development of this project, and this would be yet another sort of international project with some lessons that we have learned how to manage such a project. So, looking forward.
Thank you very much for a very exhaustive discussion.
There's a question from Praveen.
Yeah, thank you. Thank you, Professor Narayan. Dr. Abramowicz, I have a small question. The time frame of the CEPC and compact linear collider pretty much intersecting. So what will be the EU preference is going to be like?
Okay, first of all, the timelines that we received, we treated them as start from time zero, and time zero is basically when there is approval. So it's not clear to me that they are exactly on the same time scale. It's true that if we look at China, if they wanted to build the accelerator, they don't need anybody to do it. I'm talking financially. I'm not talking about so. Also, we are aware of the fact that it's science-wise, it's not completely a competition, okay? Because one thing that, and imagine that, let's do that. Let's do this, Gedanken sort of experiment. Let's assume that ILC comes up and CERN needs a new facility by 2040, okay? It probably will not be yet the Hadron-Hadron Collider because it will take more time to build the magnets. But it can quite easily shift to an E+ E- collider. So you would think there is a competition. There is no competition because, first of all, launching FCCEE after the ILC already explored the Higgs increases the statistics of the Higgs, and it starts moving towards lower energies. So basically constraining the parameters of the standard model, which enter with all the prediction and so on and so forth, and can. Now, is it fascinating? There are people who love to do precision experiments. I don't know whether, I'm talking, for example, the Z-peak measurements. Mm-hmm. I think, so again, we will always be able to argue that, this is very complementary and, we need precision, because if we don't find anything new at the LHC, we have to just increase the precision and make sure that in our next step, we will be able to see deviations, whether direct or indirect. The same goes for CLIC and CEPC, okay? CEPC is a circular machine. It has a limited, option in terms of energy. It would stop at the Higgs, maybe push it a little towards the top. CLIC can go much beyond that and also produce the Higgs self-coupling. So it's fine. If we had enough money, we could do all of them, and it would be better for everybody.
Let us hope everything will work out. Thank you.
Thank you.
On that very, very positive, hopeful note, I think we should probably close the session. So thank you, Professor Abramowicz. Fascinating talk. And thank you to all the 4 speakers for really exciting topics. So I think at this point, we should close plenary session 7. Thank you, everyone.
Thank you, Professor Narayan, for getting up so early in the morning and chairing this session. Thanks to Halina, Abhay, Phil, and Shep for this brilliant talk. So I'll take 10 more minutes because this is the best part for me to give a vote of thanks at the end of this symposium, as well as announce the best posters. So I'll just take 10 minutes. Let me share the screen. Okay, so it is my great pleasure to give this vote of thanks at the close of this symposium, an exciting scientific endeavor which we all went through. It would not have been possible without all these participants, and I see that the numbers are reaching 173, largest in a session. So thank you for staying with us for the 5 days. So first of all, thanks to the sponsors, Department of Atomic Energy, SCRB, and the organizing institutes which were in and around NICER, IOP, IIT, Utkal University, Ravancha, and IISER Barampur. Thanks a lot to the National Organizing Committee and the local organizing committee for setting up the scientific program and all possible help whenever I requested. They all did it. There was no questions asked, gave all their time and energy for this. So I'm very grateful to them. Thanks to all the colleagues who chaired the parallel special sessions, plenary sessions, getting up at different times of the day, morning, evening, afternoon. So thank you very much. Without this, it would not be possible. And thanks to many of the chairs who send me these highlights of their session. And we are putting it in the highlights page in our webpage so that if somebody has missed, can look at it. The talks, the videos are all there in the websites. Thanks to the first day when Professor Vijay Raghavan joined us in the evening. It was a very nice discussions related to mega science and experiments in India and outside. Thanks to Professor Nabha Mandal for keeping that request and really setting the tone of the symposium. And you can see we ended with these future facilities and a way to move forward. Thanks to Dr. Praveer Asthana for telling us during the general body meeting about the Mega Science Vision 2035 exercise. Certainly the session before this just now will be part of this exercise. Thank you very much. Thanks to all the plenary speakers. All the talks were fantastic. I thoroughly enjoyed it. I'm sure all the participants learned a lot and enjoyed the talks. Thanks to the mini review speakers. Several of them are young colleagues who spoke. There were also a good mixture of older colleagues who shared the experience. So thank you all for giving these review talks. Thanks to all the speakers in the special sessions. So there were sessions on our tributes to Professor Pushan Majumdar. There were tributes on, to different speakers from various fields also came and talked there. Then we had the session on gender parity aspects and how to move forward. It was very exciting discussions. Thanks to all the participants. And today we had this Rahul Basu Best Thesis Award session, and it also, we saw how exciting work these young colleagues carried out in their thesis. So thanks to you all. I must thank our director, Professor Sudhakar Panda, for giving all support for this symposium. He is part of our community. Thanks to NICER Finance and Accounts, Store and Purchase, and Institute Works Department, everything moved very nicely without any hiccups. Thanks to the Computer Center for ensuring that there is no disruptions and helping us setting up the web page, Jagjit Sahu and Dr. Varcheshwi Kashyap for taking the full load on putting things and designing the website, putting all the material there. It's by Varcheshwi and Jagjit Sahu and Ranbir did all the Zoom, YouTube and bulletins that you get in the morning and the evenings. So thank you. Thank you for all those who helped make this frame sessions for posters, online sessions. It was actually idea from Vijay Iyer, our PhD student, who although has pressing demand of finishing his PhD, but did give a lot of time. I mean, I'm really thankful to him to contributing to this. And you can see these names there of these, I think it's cartoons in the frame sessions. You must have seen them when you went around there. Thanks to these volunteers, we had to make sure that the session runs. So there were people from outside NICER who were hosts and co-hosts, and people inside, and even our master student who is now doing PhD in Rutgers, so Tanmay also chipped in from US, and all these helped run this program over the last 5 days. Thanks to you all. The proceedings will come up in International Journal of Modern Physics E and Springer Proceedings of Physics. Remember, please, the deadline is 15th March 2021. We will send out the details. It will be there in the website. And thanks to these journals for agreeing to have these proceedings published there. This is the core team without which things could not have happened. So I tried to thank them in all possible languages. Thank you for being there and bearing with me. So thank you.
I will take this opportunity to thank Professor Vedant Das Mahanti on behalf of the organizing committee and his team for bringing up this conference in a fantastic way, useful way, from choice of speakers, all the arrangements he did, and keeping the flag of Niger high. And thank you, Vedant, for all that you have done. On behalf of the community, I thank you and congratulate you.
Thank you. Thank you. Okay, so then there were, the poster actually generated quite a lot of excitement. There were training sessions to do it in frame. The A0 size posters were also prepared. So we thought we should give out some, as just a token of appreciation, and give out some best poster recognitions. And these were the colleagues who helped judge these posters at different areas. So the poster they judged in the detector and application side. One of them, the best poster is given to Samshul Haq from University of Kashmir on his RPC related work. Another, I really like this poster also, and the next one also. This was a small TPC built. I mean, it was very exciting. I spent quite a bit of time looking at it. This was also chosen as the best poster for John from TIFR, from the detector and application side. Then there was a best poster. This is on the theoretical side, Shukrut Monkar from IIT Madras. This was the committee chose this as a very interesting work on the formal theory among the posters there. Then there were posters on cosmology and particle astrophysics side. Lalit Kumar Saini from Delhi University was chosen as a token of our appreciation as a best poster. All these posters are available on the website, and the frames links are also there. Then Pethuraj Sankar Narayanan from TIFR was also chosen, his contribution was also chosen as the best poster in cosmology and particle astrophysics side. This is related to INO. Then on the neutrino physics side, Amina, sorry for the typo, Amina Khatum from, I think she was a student at Institute of Physics, now a postdoc in Slovakia, for her work in the neutrino physics. Lakshmi S. Mohan, I think she was a student at maybe math science and now at postdoc at Warsaw. Her work was appreciated by the committee who reviewed it, and as a token of our appreciation, this best poster. Then the third best poster in the neutrino physics category to Kuldeep Deka from University of Delhi. Then coming to standard model and beyond standard model, Jyotirmoy Bora from IIT Guwahati. Several of the committee members thought this was a nice work to be recognized. Then Paulami Mandal from University of Calcutta. Her work on hierarchy problem and dimension 6 effective operators, the judges felt was very interesting, very nicely laid out poster with sufficient details. So they recognized it as a best poster. Then Vibhavasu De from Institute of Physics for his work on enhancing scalar production with leptoquarks at LHC was also suggested to be given this token of appreciation. From the relativistic heavy ion collisions and QCD, this work on QGP vorticity and particle spin polarization, which has links to the current experimental, very fresh measurements by Rajiv Singh, who I think is now in Poland, got appreciation from the judges. And Ankit Kumar Panda from NICER on relativistic non-resistive viscous magnetohydrodynamics from kinetic theory, a relaxation time approach, also was suggested by several referees to be given this token of appreciation as a best poster. And one of the very interesting poster which came from the Indian group detector at LHC, at Alice at LHC. This is by Avi Modak from Bose Institute. Very nice work on the multiplicity distributions at 5 TeV at forward rapidity in P-led collisions was also judged as the best poster in the sector of relativistic heavy ion collisions and QCD. So those were the best posters. I will take this opportunity to thank my co-chair, Sanjay, who has been a great support, without which organizing things like this would not have been possible. Whenever I say anything, he just helps, and so I want to thank him. Just in case many of you do not know, he is my classmate from MSc days. 3 others also contributed to this symposium in various ways. Gagan, he's also my classmate from the same university. Sachi in PRL, and Sashanshu until now was the head of physics in Utkal University. If you are wondering about this photo, I couldn't find another one from him. And in case you think what I and Sanjay used to look at that time, this is how I used to look and Sanjay used to look around that time. And this would not have been possible without the supports of this friend. If you think that that's all, no, we have many others, my seniors and juniors. All these are from the same university. And in one way or the other, whenever I need their support, they have always been available and they have supported here. So these are all in high energy physics from the same university as I belong. Okay, so that brings me to the end. Thanks to all participants for making this event successful. I will end by sharing a mail which I got from a student at 1 AM on 18th, okay, today. And very interesting, he asked a question: since the high energy physics community in India is becoming larger, then why are we not building our own high energy accelerator facilities in India? Is there any future plan to build this? I'll generalize it to the discussions which we had on mega sciences, not only facilities, detectors, and all aspects. You can see this is a very young student, young PhD student, and that's the aspiration of the younger generation in our community. So I would just say that let's together try to achieve it, or try to really work together to achieve this vision which these young people have in their mind. So thank you for sending this email. I just thought I should share. So that's all from NICER. We are going to move to ISA Mohali, and in December, these are the tentative dates. This is what was decided at the general body meeting, and we'll see you all hopefully physically in ISA Mohali in 2022. So thank you all. And thank you for attending this symposium.
Thank you, sir.
Yes.
Thanks to the entire team.
Thank you. Okay.
It was really wonderfully organized. You've really set a very, very high standard.
And congratulations for doing it in such a difficult time. So once again, let's all meet in, presumably not virtually, the next time.
Congrats, Vedang.
Thank you.
Vedanga, it was a really nicely organized workshop.
Thank you.
I thoroughly enjoyed.
Thank you. Okay.
Okay, bye everybody.
Yeah, take care and bye.
I was very happy because it gave me a chance to see all the members of the friends in the higher energies community after a long time. Bye.
Thank you.
Bye, Vedang. Thanks a lot. Bye.
Yeah. Bye.
Bye, Vedang.
Bye.
Bye, Vedang. Nice.